Imagine standing beneath a night sky, far from any city lights, watching a silent display of distant stars. It looks peaceful, eternal, but that serenity is an illusion. Right now, across the vast expanse of the cosmos, the universe is screaming. It is a stage for events of almost incomprehensible violence, where stars are not just born, they die in spectacular, city-sized furnaces that outshine entire galaxies for a few blinding moments. These are the universe's most energetic explosions, the ultimate cosmic fireworks, and their story is written in the very elements that make up our world and ourselves. Their power is so immense that it can warp the fabric of space and time, sending ripples across billions of light years, and their beauty is born from absolute destruction. This journey we're beginning today is a voyage to the edge of physics itself, to witness events that defy our everyday understanding of reality. We will explore supernovas, the final, glorious breaths of massive stars, which seed the universe with the iron in our blood and the calcium in our bones. We will confront gamma-ray bursts, the most powerful explosion since the Big Bang, beams of energy so focused and intense that if one occurred within our galactic neighborhood, it could sterilize entire planets. These are not just abstract astronomical events, they are the fundamental forges of creation. Every time we look up, we are seeing the aftermath of these cosmic cataclysms, the scattered ashes of stellar giants that lived and died so that new stars, planets, and perhaps even life could one day emerge. So prepare to have your perspective shifted. Over the course of this video, we will uncover 50 incredible facts about these violent and beautiful phenomena. We will see how they shape the architecture of galaxies, how they challenge our deepest laws of physics, and how they connect the grandest scales of the cosmos directly to our own existence. This is a story of endings that are also beginnings, of chaos that breeds order, and of a universe that is far more dynamic and explosive than it appears from our quiet corner. The show is about to start, and it is a spectacle you will not want to miss. To truly grasp the scale of these events, we first need to understand what separates a simple stellar flare-up from a true cosmic explosion. It's the difference between a campfire and a volcanic eruption. An energetic cosmic explosion is not just a star getting brighter. It is a fundamental, catastrophic change in the object itself, a violent event that releases more energy in a few seconds or minutes than our Sun will emit over its entire 10 billion-year lifetime. This energy isn't just released as visible light. It floods across the entire electromagnetic spectrum, from long radio waves to incredibly energetic gamma rays. This tells us that the processes involved are not just about heat, but about fundamental physics being pushed to its absolute limit. The sheer diversity of these explosions is one of the most fascinating aspects. At the smaller end of the scale, we have nova. These occur in a binary star system where a dense white dwarf star steals material from its companion. This stolen hydrogen builds up on the white dwarf's surface until the pressure and temperature trigger a runaway thermonuclear explosion. This is a surface event. The star itself survives, and a nova can actually happen repeatedly. But when we talk about truly energetic explosions, we are talking about events that destroy the star completely. This brings us to the supernova, the death of a star at least 8 times more massive than our Sun. When such a star runs out of nuclear fuel, its core collapses in less than a second, rebounding in a shockwave that blasts the star's outer layers into space at velocities approaching 10% the speed of light. This explosion is so brilliant it can, for a short time, outshine the combined light of every other star in its host galaxy. And even beyond the supernova, there is an even more extreme class, the hypernova. This is thought to be the death scream of a very rare, incredibly massive star, perhaps 50 times the mass of our Sun or more. A hypernova is not just a more powerful supernova, It is a different kind of beast, often associated with the birth of a black hole and the eruption of those focused, universe-spanning death rays known as gamma-ray bursts. So, when we use the term cosmic explosion, we are referring to a spectrum of violence from stellar hiccups that merely scorch a star's surface to ultimate, transformative events that tear stars apart, forge the elements of life, and leave behind the most exotic objects in the universe. While the serene nova is a surface-level firecracker, a supernova is the complete and utter demolition of a star. It is a stellar death on the most epic scale imaginable, a final, furious act of self-immolation that, for a brief moment, can outshine the combined light of billions of its stellar neighbors. This isn't just a star getting brighter, it is a star ceasing to be, and in its death throes it becomes a cosmic engine of incredible power and creation. The energy released in those few short weeks is staggering, more than our own sun will manage to produce across its entire 10 billion-year lifespan. But to truly appreciate this cosmic drama, we need to understand that not all stellar deaths are the same. Astronomers categorize these explosions primarily into two distinct families, each with its own unique trigger and devastatingly different outcome. The first type, known as a Type I supernova, begins not with a single massive star, but with a cosmic partnership gone wrong. Picture a binary system where one star has already lived its life and settled down as a white dwarf, an incredibly dense Earth-sized remnant made mostly of carbon and oxygen. This dead star begins to pull material, primarily hydrogen, from its companion star. The stolen gas accumulates on the white dwarf's surface, increasing its mass and consequently the pressure and temperature at its core. This continues until the star approaches a critical limit known as the Chandrasekhar limit, about 1.4 times the mass of our Sun. At this precise point, the pressure in the core becomes so extreme that it ignites a runaway nuclear fusion chain reaction. The entire white dwarf, from its center to its surface, fuses its carbon and oxygen into heavier elements like iron in a matter of seconds. The star does not just explode, it is completely and utterly vaporized, leaving behind no central remnant, just an expanding cloud of brilliant, newly forged elements racing outward. The second major category is the core collapse supernova, which is the fate awaiting stars at least 8 times more massive than our Sun. These giants live fast and die young, burning through their nuclear fuel in just tens of millions of years. The drama begins deep within the star's core, which acts like a multi-layered onion. The star fuses hydrogen into helium, then helium into carbon, and so on, creating progressively heavier elements like oxygen, neon, and silicon, until the core is finally filled with iron. And here lies the catastrophe. Fusing iron does not release energy, it consumes it. The star's central engine suddenly sputters and dies, with no outward pressure from fusion to support it against its own immense gravity. The iron core collapses catastrophically. In less than a second, a core that was once the size of Earth is crushed into an unimaginably dense ball of neutrons barely the size of a city. This collapse happens so violently that it rebounds, sending a tremendous shockwave racing back outward. This shockwave blasts the star's outer layers into the depths of space at speeds exceeding 20,000 miles per second. What remains behind is not nothing, but one of the universe's most exotic objects. If the core is sufficiently massive, it collapses directly into a black hole. If it's a bit less massive, it becomes a neutron star, a teaspoon of which would weigh billions of tons on Earth. So, while a Type I supernova is a thermonuclear bomb that annihilates a dead star, a core collapse supernova is a gravitational implosion that forges a new cosmic monster from the ashes of the old. Both are titanic explosions, but they represent two fundamentally different pathways to stellar destruction, each leaving its own unique fingerprint on the cosmos. Now, having understood the two main paths to a star's destruction, we can begin to appreciate the almost mythical power these events unleash. To quantify the energy of a supernova is to grapple with numbers so vast they lose all meaning. Let's try to put it into perspective. Our Sun, a fairly average star, produces enough energy every second to meet humanity's current power needs for over 500,000 years. A supernova, in the single second of its core collapse, releases more energy than our Sun will over its entire 10 billion year lifetime. It is an outpouring of power so colossal that if you were to convert the entire mass of the Earth into pure energy using Einstein's famous equation, you would still fall far short of the fury unleashed by a single dying star. One way to visualize this is through a terrestrial, though still horrifying, comparison: the nuclear bomb. The most powerful nuclear device ever detonated, the Tsar bomber, had an explosive yield of around 50 megatons. A supernova's energy output is equivalent to detonating approximately 10 octillion of those bombs simultaneously. That's a 1 followed by 28 zeros. If you could somehow gather that many bombs, they would form a sphere larger than our entire solar system. The supernova compresses that unfathomable energy release into a shockwave that travels at a significant fraction of the speed of light, violently ejecting a star's outer layers and creating an expanding fireball of incandescent gas. This cataclysmic energy release is what gives a supernova its most stunning observable feature: its unbelievable brightness. For a period of weeks or months, a single supernova can outshine its entire host galaxy. Think about that for a moment. A typical galaxy like our own Milky Way is home to between 100 billion and 400 billion stars. A single stellar explosion, a pinprick of light within that vast cosmic city, can suddenly become brighter than all of those hundreds of billions of stars combined. This temporary brilliance is what allows astronomers to spot supernova in galaxies millions or even billions of light years away. We are not seeing the star as it is now, but as it was when its light began its journey across the cosmos, a ghostly echo of an ancient catastrophe that makes it visible across unimaginable voids. This incredible luminosity isn't just about raw power, it's also about efficiency and transformation. In its final moments, a massive star converts a substantial portion of its mass directly into energy. Furthermore, the radioactive decay of elements forged in the explosion, particularly an isotope of nickel, provides a sustained afterglow that keeps the supernova shining brightly for many weeks. It is this combination of instantaneous, violent energy release and a slower, radioactive power source that creates the brilliant beacon we observe. This ability to outshine galaxies is not just a dramatic fact, it is a crucial tool. It means that supernova act as cosmic lighthouses, allowing us to measure vast distances across the universe and probe the properties of the cosmos itself, turning a story of destruction into a key for understanding the universe's grandest scales. But the story doesn't end with the blinding flash of the explosion itself. In fact, that is merely the opening act. The brilliant light that outshines a galaxy will eventually fade over weeks and months, but what remains is the true legacy of the star, a supernova remnant. This is the expanding, glowing shell of stellar debris, the shrapnel from the cosmic detonation, and it becomes a powerful engine of creation for thousands of years to come. Picture the most famous example, the Crab Nebula. What we see today is the ghostly, filamentary aftermath of a star whose death was witnessed by Chinese astronomers in the year 1054. For nearly a millennium, that expanding cloud of gas has been racing outward at over 3 million miles per hour, a testament to the incredible force of the initial explosion. This outward blast is far from a peaceful expansion. The remnant's leading edge is a colossal shockwave, a spherical wall of energy and matter that acts like a cosmic bulldozer. As it plows into the thin gas and dust that fills the space between stars, it doesn't just push it aside, it violently compresses and heats it to millions of degrees. This interaction is what causes the remnant to glow so brilliantly across different wavelengths of light, from visible hues to X-rays. The shock wave also does something profoundly important. It seeds the surrounding space with turbulence. By compressing these interstellar clouds, it can trigger the gravitational collapse necessary for new stars to be born. In a very real sense, the death of one star can be the midwife for the birth of many others. Most critically, supernova remnants are the universe's ultimate recycling plants. Remember all those heavy elements forged in the star's core during its life and synthesized in the incredible heat of the explosion itself. Elements like oxygen, carbon, iron, silicon, and even gold are now scattered far and wide. The supernova remnant is the delivery mechanism, hurling this newly created material across light years of space. Before the first stars lived and died, the universe was composed almost entirely of hydrogen and helium. There were no rocks, no metals, no complex chemistry. Every single atom of oxygen you breathe, every particle of carbon that forms the basis of life, every speck of iron in your blood, was once forged in the heart of a massive star and then blasted into the cosmos by a supernova. We are literally made of stardust, and supernova remnants are the distribution system that delivered those essential ingredients. Over tens of thousands of years, the remnant will continue to expand, gradually slowing down and cooling until its material finally mixes with the general interstellar medium. This enriched gas, now pregnant with the elements for planets and life, will eventually coalesce into a new generation of stars. Our own solar system formed from such a cloud that had been fertilized by the debris of countless ancestral supernovae. So when we gaze at the intricate tapestry of a supernova remnant, we are not just looking at a beautiful cosmic relic. We are witnessing the continuous cycle of cosmic death and rebirth, a process that turns destruction into the very foundation for new worlds and future possibilities. While the expanding cloud of a supernova remnant spreads its elemental bounty across space, the story at the very center of the explosion is often even more incredible. When a massive star undergoes a core collapse supernova, not all of it is blown away. The fate of the incredibly dense core that remains is a tale of physics pushed to its absolute limit, leading to the formation of one of the universe's most bizarre objects, the neutron star. Imagine taking the entire mass of our Sun, a sphere nearly 900,000 miles across, and crushing it down into a perfect ball just 12 miles wide, roughly the size of a city. The forces involved in this transformation are so extreme that they fundamentally alter the very nature of matter itself. This process creates a substance with a density that is almost impossible to comprehend. In a neutron star, the immense gravitational pressure is so overpowering that it forces electrons and protons to merge, transforming almost the entire object into a sea of neutrons. There are no atoms with empty space between them. It is essentially one gigantic atomic nucleus. To put this density into perspective, a single sugar cube-sized piece of a neutron star would weigh approximately 1 billion tons on Earth. That is the equivalent of squeezing Mount Everest into a small, carry-on suitcase. The surface gravity is so intense that if you were to drop a marshmallow onto it from just a meter away, it would impact with the energy of 1,000 hydrogen bombs. This isn't just a dead star, it is a laboratory for states of matter that cannot exist anywhere else in the universe. But the strangeness doesn't stop with its unimaginable density. Some neutron stars exhibit one of the most precise and useful behaviors in all of astronomy. They become pulsars. This happens when a neutron star is born spinning at a tremendous rate, sometimes completing hundreds of rotations every single second. Coupled with this rapid spin is an unimaginably powerful magnetic field, trillions of times stronger than Earth's. This magnetic field funnels intense beams of radiation, from radio waves to gamma rays, out from its magnetic poles. If the star's rotation axis is tilted compared to its magnetic axis, these beams sweep through space like the beams of a cosmic lighthouse. From our perspective on Earth, if one of these beams happens to sweep across our line of sight once per rotation, we detect a very regular, very precise pulse of energy. The timing of these pulses is astonishingly reliable, rivaling the accuracy of atomic clocks. The first pulsars discovered were nicknamed LGM for little green men because their perfect regularity initially suggested an artificial, intelligent source. We now know they are the natural clocks of the universe, and their discovery provided the first direct evidence for the existence of neutron stars. These cosmic lighthouses allow astronomers to perform incredible feats of measurement, from testing Einstein's theory of general relativity to mapping the structure of our galaxy, all by listening to the steady, rhythmic ticking of a stellar corpse spinning in the void. And just when we thought neutron stars represented the ultimate frontier of stellar density, the universe reveals an even more spectacular event. If the formation of a single neutron star is a dramatic collapse, then the collision of two of them is a cataclysm of almost unimaginable scale. This is the kilonova, an explosion that, while visually fainter than a supernova, unleashes a unique and profoundly important form of cosmic violence. Picture two city-sized objects, each containing more mass than our Sun, locked in a lethal gravitational dance. They spiral inward over millions of years, radiating energy in the form of ripples in space-time known as gravitational waves, until they finally slam together at a significant fraction of the speed of light. The moment of impact is not a simple merge. It is an incredibly violent and complex event that shreds the neutron stars apart. The collision creates a ferociously hot, dense soup of neutrons and other subatomic particles, an environment more extreme than anything we can replicate on Earth. For a brief period, this maelstrom can form an incredibly massive, rapidly spinning neutron star or collapse almost instantly into a black hole. But the true magic happens in the material that gets flung outward from the collision. This ejected material is incredibly rich in neutrons, and in this neutron-rich environment, atomic nuclei can capture neutrons at a staggering rate, a process known as rapid neutron capture, or the R process. This is where the kilonova earns its name and its cosmic significance. The R process is responsible for creating roughly half of all the elements heavier than iron in the entire universe. While supernovae are fantastic at producing elements like oxygen, silicon, and iron, they struggle to build the very heaviest atoms. A kilonova, however, is the universe's primary forge for elements like gold, platinum, and uranium. The radioactive decay of these newly synthesized heavy elements powers the kilonova's transient glow, which typically shines for about a week and is most prominent in infrared light. This is why, despite the immense energy involved, a kilonova appears visually faint compared to a supernova. Its light is redder and spread over a different part of the spectrum. The first confirmed observation of a kilonova in 2017 was a landmark event in astronomy, not just for what we saw, but for what we heard. For the first time, astronomers detected the gravitational waves from the inspiral of two neutron stars simultaneously with the gamma-ray burst and the visible light from the explosion itself. This multi-messenger astronomy provided direct, irrefutable evidence linking neutron star mergers to the production of heavy elements. By studying the light from that event, scientists were able to identify the spectroscopic fingerprints of heavy elements like gold and platinum, confirming that the dazzling jewelry we wear and the uranium that powers nuclear reactors were born in the chaotic aftermath of these incredible cosmic collisions. Each kilonova is a brief but prolific factory, seeding the galaxy with the precious materials for future planets and potentially for life itself. This direct connection between cosmic violence and human existence brings us to one of the most profound facts about these explosions. The very gold in a wedding band or a pair of earrings, a symbol of permanence and beauty here on Earth, has the most dramatic and temporary of origins. It was forged in a cataclysm that lasted mere seconds, an event we now call a kilonova. The story of how this happens is a tale of nuclear physics operating under the most extreme conditions imaginable, a process that solves one of the universe's great elemental mysteries. For decades, astronomers puzzled over the origin of the heaviest elements in the periodic table. We knew that stars like our Sun fuse hydrogen into helium, and that massive stars can build elements up to iron in their cores. But creating anything heavier than iron is a problem. Fusing iron actually consumes energy instead of releasing it, so it cannot power a star. Elements like gold, platinum, and uranium require a special kind of nuclear cookery, one that involves a massive flood of free neutrons. This is where the kilonova becomes the universe's ultimate alchemist. The key is a mechanism known as the rapid neutron capture process, or the R process for short. Imagine the aftermath of two neutron stars colliding. The incredible violence of the impact blasts a small but incredibly dense and hot cloud of material into space. This ejected material is essentially a soup of free neutrons, the building blocks of atomic nuclei, ripped from the neutron stars themselves. In this environment, existing atomic nuclei are bombarded by an immense wave of neutrons. They capture these neutrons so quickly that the nucleus doesn't have time to stabilize through radioactive decay before capturing the next one. It's a frantic, rapid-fire assembly line that shoots lightweight nuclei up the periodic table in a matter of seconds, transforming them into the heaviest elements we know. The radioactive decay of these newly forged, unstable heavy elements is what actually powers the kilonova's brief glow. This is why the event shines most brightly in infrared light for about a week. The dense cloud of heavy elements blocks visible light but radiates heat. The confirmation of this theory was a monumental achievement in modern astronomy. In 2017, the LIGO and Virgo observatories detected gravitational waves from a neutron-star merger, and telescopes around the world and in space swiveled to observe the same patch of sky. What they saw was the first multi-messenger signal of a kilonova, and the spectral analysis of its light revealed the unmistakable fingerprints of heavy elements like gold and platinum being created in real time. So consider the journey of a single atom of gold. It was born in the frenzied seconds following a collision that occurred perhaps billions of years ago in a galaxy far away. That atom was then flung out into the interstellar medium, eventually becoming part of a vast cloud of gas and dust. Over eons, that cloud collapsed to form a new solar system, and that atom of gold found its way into the rocky material of a young planet. Millions of years of geological activity concentrated it into a vein, which was finally mined and shaped by human hands. The gold we treasure is not just a metal, it is stardust of the most exotic kind, a tangible piece of a cosmic catastrophe that connects us directly to the most violent and creative forces in the universe. Yet even the awesome power of a supernova or the elemental alchemy of a kilonova is dwarfed by a phenomenon that represents the absolute peak of cosmic violence. If a supernova is a nuclear bomb, then a gamma-ray burst is the detonation of an entire stellar arsenal. These events are the true titans of explosive energy, the most powerful electromagnetic blasts the universe has produced since its own birth in the Big Bang. Their defining characteristic is their breathtaking brevity. A gamma-ray burst can appear without warning, flood space with incomprehensible levels of radiation for a few fleeting seconds, and then vanish forever, leaving behind only a fading afterglow. In that brief window, a single gamma-ray burst can concentrate more energy than our Sun will radiate across its entire 10 billion-year journey from birth to death. To grasp the sheer intensity of this energy release, we need to think about focus and concentration. A supernova is like a massive, omnidirectional explosion, its power radiating outward in all directions like an expanding sphere. A gamma-ray burst, however, is more like a cosmic blowtorch. Its energy is channeled into two extremely narrow, oppositely directed jets that travel at over 99.99% the speed of light. This means that instead of the energy being diluted across a vast sphere, it is focused into two incredibly tight beams. If you were standing anywhere within the path of one of those jets, you would witness an energy flux that defies description. Outside that narrow cone, however, you might not notice anything particularly unusual about that patch of sky. This beaming effect is why gamma-ray bursts can appear to be so phenomenally luminous. All of their catastrophic power is concentrated into a pencil-thin beam of pure destruction. The fleeting nature of these events, lasting from mere milliseconds to several minutes, presented a massive challenge to astronomers for decades. They were first discovered quite by accident in the late 1960s by American Vela satellites, which were designed to monitor for clandestine nuclear weapons tests in violation of the Atmospheric Test Ban Treaty. The satellites began detecting intense bursts of gamma rays coming from deep space, not from Earth, and their origin was a complete mystery. Because the bursts were so short-lived and seemed to come from random directions, pinpointing their source was nearly impossible with the technology of the time. It wasn't until the 1990s, with the launch of dedicated satellites like NASA's Compton Gamma Ray Observatory, that astronomers could quickly determine their rough positions and alert other telescopes to search for a fading afterglow in X-ray, visible, and radio light. This afterglow, which can persist for days or weeks, was the key that finally unlocked the distance to these events, revealing that they were not happening in our own galaxy, but were instead cosmological, occurring in galaxies billions of light-years away. This confirmed their almost unbelievable power, as they had to be intrinsically brilliant to be visible from such incredible distances. This incredible power and fleeting nature naturally lead us to a key discovery that helped unravel their mystery. For a long time, gamma-ray bursts seemed to be a chaotic collection of events, but astronomers eventually noticed a clear pattern in their durations. They don't occur on a smooth spectrum. Instead, they distinctly cluster into two primary families, a finding that was a major breakthrough in understanding their origins. This bimodal distribution separates them into what are known as long-duration and short-duration gamma-ray bursts, and this simple distinction of time points directly to two completely different cosmic catastrophes. Let's start with the long-duration bursts, which are the more common of the two. These events last for more than 2 seconds, and many can shine for several minutes, with the record holder glowing in gamma rays for almost an hour. The leading model for what causes these epic events is called the collapsar model. It begins with a very specific kind of star, a Wolf-Rayet star, which is a colossal, rapidly spinning star at least 25 times more massive than our Sun. This star has already shed its outer layers of hydrogen, leaving behind a bare core of heavy elements. When this giant finally runs out of fuel, its core collapses directly into a black hole, just like in a regular supernova. But the rapid rotation of the star is the critical ingredient that transforms a simple collapse into a gamma-ray burst. As the core implodes, the infalling material doesn't just vanish into the newborn black hole. Instead, it forms a superheated, magnetized disk of plasma spinning furiously around the event horizon. The incredible physics at play here then focuses and accelerates some of this material into two jets that fire out from the star's poles at nearly the speed of light. These jets are so powerful and focused that they must literally drill their way out through the body of the star itself. The gamma-ray burst we detect is the moment these ultra-relativistic jets finally break free from the stellar surface. Because the star is so massive, this process of punching through takes time, which is why we observe a long-duration burst. The event is often accompanied by a supernova, though one that is often unusually energetic, sometimes called a hypernova. So, a long gamma-ray burst is essentially the birth cry of a new black hole, a signal that a stellar giant has died in the most violent way possible, its death beam sweeping across the universe. On the other side of the timeline are the short-duration gamma-ray bursts. These events are far more fleeting, typically lasting less than 2 seconds and often only a few tenths of a second. Their brevity is a direct clue to their origin, which involves objects that are much, much smaller than massive stars. The primary source for short GRBs is the merger of two compact objects, such as two neutron stars or a neutron star and a black hole. Remember the kilonova we discussed earlier? A short gamma-ray burst is the initial, incredibly intense flash that accompanies that collision. Picture two neutron stars, each the mass of the Sun compressed into a city-sized ball, spiraling ever closer. Their final moments are a frenzy of gravitational waves and tidal forces. When they finally make contact, the merger is instantaneous and violently efficient. Just as with the quasar model, the merger is thought to form a black hole almost immediately, surrounded by a brief, hot disk of leftover neutron star material. Again, jets are launched from the poles of this system. However, because there is no massive stellar envelope to bore through, the jets can escape almost instantly. The entire energetic release is compressed into a very short, sharp burst of gamma rays. The afterglow of a short GRB is then the kilonova, the glowing cloud of heavy elements created in the merger's aftermath. The historic detection in 2017 was, in fact, a short gamma-ray burst, forever linking these brief flashes of light to the cosmic forges of gold and platinum. This clear division by duration has given astronomers a powerful taxonomic tool, allowing them to listen to the different ways the universe screams and to understand the specific cataclysmic events that generate each type of powerful signal. The incredible power of a gamma-ray burst, enough to outshine a supernova, all comes down to a matter of focus. It's the fundamental difference between a firecracker and a laser. While a supernova explodes in a roughly spherical manner, sending its energy out in all directions, a gamma-ray burst channels its entire catastrophic output into two of the most focused beams in the universe. These are known as relativistic jets, and their existence is what transforms a stellar catastrophe into a universe-spanning spotlight of pure energy. The term relativistic is key here. It means these jets travel at velocities so close to the speed of light that the strange effects of Einstein's theory of relativity dominate their behavior. We're talking about speeds exceeding 99.99% of light speed. To understand how these jets form, we need to look at the engine at the heart of the explosion. Whether it's the collapse of a massive, rapidly spinning star or the merger of two neutron stars, the result is the same: the birth of a newborn black hole. But this isn't a quiet event. As material catastrophically falls toward the black hole, it doesn't just vanish silently over the event horizon. Instead, it forms an incredibly hot, magnetized, and dizzyingly fast spinning structure called an accretion disk. This disk acts like a cosmic hurricane, with material swirling around the black hole at fantastic speeds. The physics within this maelstrom are extreme, generating intense magnetic fields and creating powerful frictional forces that heat the plasma to temperatures of billions of degrees. It is from the poles of this system, perpendicular to the accretion disk, that the jets are launched. The exact mechanism is still an area of active research, but it's believed that the intense magnetic fields get wound up like cosmic springs, channeling some of the infalling material and a tremendous amount of energy away from the disk and focusing it into two narrow columns. Another possibility involves the extraction of rotational energy directly from the black hole itself. These jets then blast their way outward. In the case of a long burst from a collapsing star, the jets must physically drill through the remaining outer layers of the star, which takes several seconds and explains the longer duration. For a short burst from a merger, there's no massive envelope to penetrate, so the jets escape almost instantly. The consequences of this beaming are profound. Because the energy is not spread out in a sphere but concentrated into jets that may be only a few degrees wide, the intensity along the beam's axis is amplified to almost unimaginable levels. If you could somehow measure the brightness from within the jet, it would be far greater than the luminosity we infer from a distance. This also means that for every gamma-ray burst we detect, there are countless others whose jets are pointed in other directions, completely invisible to us. We only see the ones where the cosmic lighthouse beam happens to sweep across our line of sight. This focused power is what makes a gamma-ray burst so dangerous on a galactic scale. If one were to occur within a few thousand light-years of Earth and we were caught in the crosshairs of its jet, the radiation could strip away our planet's ozone layer, potentially triggering a mass extinction. The relativistic jet is the universe's ultimate precision instrument of destruction, turning a stellar death into a targeted ray of pure cosmic power. This focused power of the relativistic jet, a cosmic blowtorch of pure energy, leads us to a sobering and deeply fascinating possibility. What if such an event happened not in a distant galaxy, but in our own cosmic backyard? This is the grim reality behind what astronomers sometimes call the Death Star beam threat. While the odds are incredibly low, the consequences of a gamma-ray burst occurring within a few thousand light-years of Earth, with its jet pointed directly at us, would be nothing short of a planetary-scale catastrophe. To understand the mechanism of this threat, we need to look at what would actually happen when that beam of high-energy radiation arrives. It wouldn't be a slow, creeping danger. Traveling at the speed of light, the first sign would be the gamma rays themselves, an invisible, silent flash of immense power hitting our atmosphere. This initial blast would not heat the planet or cause fiery explosions on the ground. Instead, it would initiate a complex and devastating chemical chain reaction in the upper atmosphere. The gamma rays would smash into air molecules, breaking apart nitrogen and oxygen and creating a soup of highly reactive nitrogen oxides. These compounds are brutally efficient at destroying ozone. In a matter of just days or weeks, the gamma-ray burst could chemically shred Earth's protective ozone layer, depleting it by 50% or more. This layer is our planet's primary shield against the sun's harmful ultraviolet B and UVC radiation. With that shield gone, the surface of the Earth would be bathed in an intense, mutagenic UV glow. The immediate biological impact would be most severe on the base of the food chain. Phytoplankton in the oceans, which produce a significant portion of the world's oxygen and form the foundation of the marine ecosystem, are highly vulnerable to increases in ultraviolet radiation. A massive die-off of these microscopic organisms would trigger a collapse that would ripple upward through the entire ocean food web. On land, plants would suffer from radiation damage, stunting their growth, while animals, including humans, would face severe sunburns, an explosion in skin cancers, and potential blindness from the increased UV exposure. The long-term effect would likely be a mass extinction event, rivaling the great die-offs in Earth's history, all caused by a stellar explosion that might have occurred thousands of years before the light and the danger ever reached us. This leads to a compelling and eerie question for paleontologists and astronomers. Could such an event have already happened? Some scientists have speculated that a past mass extinction, particularly the Ordovician-Silurian extinction event around 440 million years ago, might bear the fingerprints of a gamma-ray burst. This extinction was unusual. It primarily affected marine life living in shallow waters and near the surface, which is precisely the kind of pattern you would expect from a sudden surge in ultraviolet radiation. While the cause of the Ordovician extinction is still debated, with other leading theories involving glaciation and climate change, a nearby gamma-ray burst remains a plausible, albeit unproven, suspect. The evidence would be subtle and hard to find after so much time, but the hypothesis serves as a powerful reminder that the evolution of life on Earth may have been shaped not just by terrestrial events, but by the violent whims of the cosmos. The universe is not a passive backdrop, it is an active and sometimes dangerous participant in our story. But the fleeting brilliance of the initial gamma-ray flash is only the beginning of the story for astronomers. That sudden, intense signal is like a cosmic alarm bell, but it rings for such a short time that it provides very little information on its own. The real detective work, the part that has unlocked the deepest secrets of these explosions, begins after the main event fades. Scientists hunt for what they call the afterglow, a slowly fading ember that glows across the universe for days, weeks, or even months. This afterglow is the key that transforms a mysterious blip of data into a rich, detailed cosmic crime scene investigation. The creation of this afterglow is a direct result of the incredible power of the relativistic jet. After the jet has broken free from its source, whether a collapsing star or merging neutron stars, it doesn't just travel through empty space. It plows into the thin wisps of gas and dust that exist in the interstellar medium. The jet is moving at almost the speed of light, so this collision is anything than gentle. It's a violent impact that creates a tremendous shockwave, both within the jet itself and in the surrounding material it slams into. This shockwave acts like a natural particle accelerator, energizing electrons to near light speeds and forcing them to spiral along magnetic field lines. This process, known as synchrotron radiation, causes the material to glow brilliantly across a wide spectrum of light, from high-energy X-rays down to long radio waves. This multi-wavelength glow is the afterglow we detect, and its behavior over time tells a detailed story about the explosion's energy, the density of its surroundings, and the nature of the jet itself. The practical hunt for an afterglow is a race against time, a global effort of coordination between spacecraft and ground-based observatories. It starts with a satellite like NASA and Neil Gehrels Swift Observatory or the Fermi Gamma Ray Space Telescope, which are specifically designed to detect the initial gamma-ray flash. Within seconds of a detection, these satellites automatically calculate a rough position in the sky and send out alerts to astronomers worldwide. This triggers a frantic scramble. Robotic telescopes on the ground swing into action, scanning the indicated patch of sky for a new pinprick of light that wasn't there before. The first afterglow to be spotted is usually in X-rays, which can be detected by instruments on the Swift satellite itself just minutes after the burst. Then, as hours pass, the emission typically peaks in ultraviolet light, then visible light, and finally radio waves. Capturing this fading light is absolutely critical. By measuring the precise position of the afterglow, astronomers can point the world's most powerful telescopes, like the Hubble Space Telescope or the Keck Observatory in Hawaii, toward it. With these immense instruments, they can obtain a spectrum of the afterglow's light, which acts like a fingerprint. This spectrum reveals the afterglow's redshift, a measure of how much the light has been stretched by the expansion of the universe, which directly tells us the burst's distance. It was the measurement of afterglow redshifts in the late 1990s that finally confirmed gamma-ray bursts were not local events in our galaxy, but were instead occurring in far-off galaxies billions of light-years away, cementing their status as the most powerful explosions in the cosmos. Furthermore, by studying the host galaxy where the afterglow resides, scientists can determine what kind of galactic environment gives rise to these catastrophic events, whether it's a region of active star formation perfect for massive collapsars or an older, quieter neighborhood where binary neutron stars might finally spiral together. The humble afterglow, a faint and fading echo, is truly the messenger that brings the story of the explosion home. But what happens when a star is so incredibly massive that even a standard core collapse supernova seems like an understated finale? This brings us to the theoretical heavyweight champion of stellar explosions, a class of events so powerful they needed their own name, the hypernova. Think of it as a supernova on steroids, an eruption of energy that pushes the boundaries of what we believe is physically possible for a single star. While a typical supernova might release around 10 to the 44 joules of energy, a hypernova is thought to be at least 10 times more powerful, and in some extreme cases, it could be up to 100 times more energetic. This isn't just a brighter flash, it represents a fundamentally different kind of stellar death, one that is intrinsically linked to the most powerful explosions we have ever detected, the long-duration gamma-ray burst. The key ingredient for a hypernova is a star of almost mythical proportions. We are no longer talking about a star just 8 times the mass of our Sun. A hypernova candidate is a true behemoth, a star perhaps 50, 80, or even over 100 times more massive than the Sun. Such stars live extraordinarily fast and furious lives, burning through their nuclear fuel in only a few million years. Their immense gravity creates cores of unbelievable density and temperature, leading to a final collapse that is far more violent than anything a smaller star could produce. In a standard core collapse supernova, the imploding core rebounds to form a neutron star. But in the case of these ultra-massive stars, the core is so heavy that even a neutron star cannot support it. There is no rebound, no second chance. The collapse is absolute. The core plunges directly through the neutron star phase and forms a black hole instantaneously. It is this direct formation of a black hole that sets the stage for the hypernova's incredible energy release. As the stellar material continues to rain down onto the newborn black hole, it doesn't just vanish quietly. Instead, it forms an accretion disk of unimaginable heat and density, spinning at a significant fraction of the speed of light. The rapid rotation of the star, a crucial legacy from its birth, is channeled into this disk, powering a dynamo that launches those focused relativistic jets we discussed earlier. In a hypernova, these jets are not just an afterthought, they are the main event. The energy required to blast these jets through the remaining star is what contributes to the explosion's extraordinary power, creating the gamma-ray burst we observe and an accompanying supernova that is itself unprecedentedly luminous. This entire cataclysmic sequence, the direct collapse to a black hole, the formation of a super-accretion disk, and the jet generation is what distinguishes a hypernova from its less energetic cousins. It is a stellar death that leaves no remnant star, only a void and a pair of cosmic blowtorches that announce its passing across the universe. But the concept of a hypernova, as extreme as it is, still leaves behind a black hole, a silent monument to the star's immense gravity. What if there existed a stellar explosion so utterly violent, so complete in its destruction, that it leaves nothing behind at all? Not a neutron star, not a black hole, not even a remnant. The star would simply vanish in a fireball of its own making. This is not science fiction. It is a theoretical possibility known as a pair instability supernova, and it represents perhaps the most absolute form of stellar death the universe can conceive. To trigger this ultimate self-annihilation, a star must be almost unbelievably massive, tipping the scales at over 130 times the mass of our Sun. The chain of events leading to this total disintegration begins deep within the star's core, which is furiously fusing elements to hold off gravitational collapse. In such a colossal star, the core becomes unimaginably hot. As it begins to fuse oxygen, the temperatures skyrocket to well over 1 billion degrees. At these extremes, the very nature of light and matter inside the star changes. The core is flooded with incredibly energetic gamma-ray photons, which typically provide an outward radiation pressure that helps support the star against its own weight. But here, something strange and catastrophic occurs. The energy of these gamma rays becomes so high that when they collide, they can spontaneously transform into pairs of particles, an electron and its antimatter counterpart, a positron. This is a direct demonstration of Einstein's E equals mc squared, with energy converting directly into matter. This seemingly esoteric particle physics has a devastating consequence for the star. Radiation pressure is a crucial component of the star's internal support structure. When gamma rays turn into matter-antimatter pairs, that supportive pressure suddenly drops. It's as if a vital pillar holding up a building instantly turned to sand. With this pressure support gone, the core can no longer resist the star's immense gravity. It begins to contract rapidly. This contraction, however, doesn't lead to a calm collapse. Instead, it causes the temperature and density to soar even further, which in turn accelerates the fusion reactions in a runaway feedback loop. The entire core becomes a single, gigantic thermonuclear bomb. The result is not a collapse, but a titanic explosion that makes even a hypernova seem restrained. The runaway fusion reaction unleashes so much energy that it overwhelms the star's gravitational binding energy, the very force that holds it together. The entire star is blasted apart from its core to its outer layers in a thermonuclear fireball of unimaginable scale. Every single bit of the star is vaporized and hurled into space. There is no lingering core, no compact object left behind. The star is completely and utterly obliterated, leaving only an expanding cloud of newly synthesized elements as evidence that it ever existed. These explosions are thought to be responsible for seeding the early universe with very specific heavy elements. Because the explosion is so complete and so hot, it can produce enormous quantities of elements like silicon, calcium, and titanium, which are then scattered far and wide to become the building blocks for future generations of stars and planets. The pair instability supernova is the universe's most definitive statement on stellar death, a final, total erasure that is simultaneously an act of profound creation. While the theoretical pair instability supernova represents a kind of ultimate stellar explosion, astronomers were stunned to witness an event that seemed to defy even those extreme models. In 2015, a robotic survey of the sky known as the All-Sky Automated Survey for Supernova, or ASAS-SN for short, detected something truly extraordinary. Designated Assassin 15LH, this object erupted in a distant galaxy and immediately shattered all records. At its peak, it shone with a luminosity of about 570 billion times that of our Sun. To put that almost meaningless number into some perspective, it was roughly twice as bright as the previous record holder and 20 times more luminous than the entire output of our 100 billion star Milky Way galaxy. This wasn't just a bright supernova, it was an astronomical anomaly of the highest order, an event so powerful that it forced scientists to question everything they thought they knew about stellar deaths. The immediate challenge was to explain the engine behind such an incredible outpouring of energy. The initial hypothesis pointed toward the most powerful supernova mechanism conceivable, a pair instability event. Perhaps this was the death of a true primordial giant, a first-generation star with a mass of 200 suns or more, finally meeting its end in the modern universe. The sheer amount of radioactive nickel required to power such a brilliant blast would have been staggering, perhaps several times the mass of our entire Sun forged in the explosion. For a while, this explanation, while extreme, seemed to be the best fit for the data. It was a tantalizing glimpse of a type of stellar death that was thought to have occurred mostly in the early cosmos. However, as astronomers continued to monitor Assassin 15LH with the world's most powerful telescopes, including the Hubble Space Telescope, the story began to change. The supernova's behavior over time didn't perfectly match the slow fade expected from a pair instability event. More crucially, the location of the explosion presented a major puzzle. It had occurred not in a star-forming region where massive young stars are born, but in the heart of a large, red and passively evolving galaxy, the kind of place where massive stars are exceedingly rare. This was like finding a volcanic eruption in the middle of a calm desert. It just didn't fit the environment. The strangeness of its location pointed toward a different, even more dramatic possibility. The leading theory that has since emerged is that Assassin 15LH may not have been a supernova at all in the traditional sense. Instead, it might have been an example of one of the most violent events a star can experience, a tidal disruption event, but on a scale never before seen. In a typical tidal disruption event, a star wanders too close to a supermassive black hole at the center of a galaxy. The black hole's immense gravity creates a tidal force so strong that it stretches the star horizontally and compresses it vertically, literally pulling it apart into a long stream of gas, a process often called spaghettification. This gaseous debris then swirls around the black hole, heating up to incredible temperatures and glowing brilliantly as it is consumed. What made Assassin 15LH so special, according to this model, was the nature of the black hole involved. It wouldn't be an ordinary supermassive black hole, but a very rare, rapidly spinning supermassive black hole, perhaps weighing in at millions of times the mass of our Sun. If a star like our Sun was torn apart by such a monster, the physics of the spinning black hole could funnel the infalling material into an exceptionally bright, sustained eruption of light, potentially matching the incredible luminosity observed. This scenario elegantly explains the location in the galactic center and some of the peculiarities in the light curve that a supernova model struggled with. The case of Assassin 15LH remains open, a testament to the fact that even with all our advanced technology, the universe is still capable of presenting us with events that challenge our fundamental classifications and push the boundaries of what we believe is possible. Now, after exploring these titans of cosmic destruction, it's fascinating to turn our attention to a different class of stellar eruption, one that represents a dramatic tempering of the violence we've discussed so far. While a supernova is a star's final, suicidal detonation, a nova is more like a star having a recurring, powerful temper tantrum. It is a surface-level explosion that leaves the star fundamentally intact, ready to build up to the same spectacular outburst again in the future. The key to understanding a nova lies not in a single, dying giant, but in the complex gravitational dance of two stars orbiting one another in a binary system. The most common scenario involves a white dwarf and a more typical star like our Sun, locked in a close embrace. The white dwarf, remember, is the Earth-sized, incredibly dense corpse of a star that has already exhausted its nuclear fuel. Its immense gravity acts like a cosmic vacuum cleaner, relentlessly pulling hydrogen-rich gas from the outer layers of its companion star. This stolen material doesn't just fall directly onto the white dwarf's surface. Instead, it forms a swirling, superheated disk of gas called an accretion disk, funneling the hydrogen down onto the white dwarf's surface. Because the white dwarf's gravity is so intense, this accumulating layer of hydrogen becomes incredibly compressed and heated. For a while, the white dwarf's dense interior simply absorbs the heat. But this cannot last forever. The pressure and temperature at the base of this hydrogen layer continue to rise, eventually reaching a critical tipping point of around 20 million degrees. At this threshold, the hydrogen nuclei, which have been packed together so tightly, can no longer resist. They ignite in a sudden, runaway thermonuclear fusion reaction, the same process that powers stars, but here it occurs in an uncontrolled blast across the white dwarf's surface. The result is a brilliant, rapid increase in brightness. The star can become 50,000 to 100,000 times more luminous than our Sun, shining as a new star, which is what nova means in Latin, in a part of the sky where nothing so bright was visible before. This isn't the star being destroyed, it's just its surface being blasted into space in a powerful flash. The white dwarf itself, protected by its degenerate core, remains completely unscathed by the surface explosion. After the outburst fades over weeks or months, the entire cycle can begin again. The white dwarf resumes its steady theft of hydrogen from its companion, slowly building up a new fuel layer on its surface, destined to ignite in another nova explosion perhaps thousands or tens of thousands of years in the future. This repeatable nature makes nova a predictable and fascinating class of cosmic explosion, a periodic reminder of the dynamic interactions happening in binary systems throughout our galaxy. This recurring nature of nova leads us to a very special and suspenseful subclass of these stellar outbursts, the recurrent nova. While many nova might repeat over immense timescales of tens to hundreds of thousands of years, a handful of systems have been caught in the act multiple times within a human lifetime. These are not just curiosities, they are cosmic ticking time bombs offering us a front-row seat to a process that could, under the right conditions, lead to a far more catastrophic and final explosion. Perhaps the most famous example is a star system known as T Coronii Borealis, or TCRB for short, often nicknamed the Blaze Star. Nestled within the small, semicircular constellation of Corona Borealis, this star system is normally far too faint to see with the naked eye. But roughly every 80 years it does something spectacular. It erupts, becoming suddenly as bright as the North Star Polaris for about a week before fading back into obscurity. The last time this happened was in 1946, which means, based on its cycle, it is due for its next performance at any moment. Astronomers around the world are watching TCRB intently, knowing that the next alert could come tonight, next week, or in the next few years, turning a quiet patch of sky into a temporary beacon. What makes recurrent nova like TCRB so special is the rate of fuel delivery. In these systems, the companion star is typically a red giant, a large, puffed-up star that is losing its outer layers quite readily. This provides a generous and steady flow of hydrogen-rich material onto the white dwarf. The white dwarf is also particularly massive, which means its surface gravity is even stronger, compressing the accreted hydrogen more efficiently and raising its temperature faster. This potent combination of a high mass transfer rate and a massive white dwarf means the critical pressure and temperature needed for a thermonuclear blast is reached much more frequently, on a scale of decades rather than millennia. Each eruption blasts away the accumulated hydrogen shell, but the underlying white dwarf remains, and the process of accretion begins again almost immediately, setting the clock for the next explosion. This predictable cycle makes them invaluable natural laboratories. By studying the light and spectra before, during, and after an eruption, astronomers can precisely measure the mass of the white dwarf, the rate of accretion, and the composition of the ejected material, fine-tuning our models of how all nova work. However, this repetitive cycle hides a deeper, more ominous potential. The ultimate fate of a recurrent nova system hinges on a delicate cosmic balance. In a perfect cycle, the nova explosion ejects exactly the same amount of mass that was accreted from the companion star. The white dwarf's mass remains stable, and the system can continue its periodic fireworks indefinitely. But what if the balance is off? What if, after each eruption, the white dwarf manages to hold onto a tiny fraction of the material that was supposed to be blasted away? Over thousands of eruption cycles, these tiny increments of mass would slowly but steadily increase the white dwarf's total weight. This is where the story takes a dramatic turn from a recurring flare up to a countdown to total annihilation. Every recurrent nova system is a potential progenitor for a Type I supernova, the very same kind of titanic thermonuclear explosion we discussed earlier that completely vaporizes a white dwarf. The trigger is the Chandrasekhar limit, that critical threshold of about 1.4 times the mass of our Sun. If the white dwarf's mass creeps up to this limit through this slow accretion, its fate is sealed. The internal pressure becomes so overwhelming that it can no longer support itself as a degenerate object. Instead of a surface explosion, the entire star, from its core to its surface, undergoes runaway carbon fusion. The white dwarf does not experience a nova. It is utterly obliterated in a supernova that, for a few weeks, can outshine its entire host galaxy. This transformation from a periodic nuisance to a galaxy-shaking cataclysm is what makes studying recurrent nova so crucial. They are the only systems where we can observe the pre-supernova accretion process in action. By monitoring stars like T Coronii Borealis, we are essentially watching a supernova precursor in its active phase, giving us unprecedented insight into the final steps that lead to one of the universe's most important standard candles. So, the next time you hear that the blaze star has erupted, remember that you are witnessing more than just a bright new star. You are seeing a test of cosmic balance, an event that could, in the far future, be the prelude to a far grander final act. While we have been journeying across the cosmos to witness stellar cataclysms in distant galaxies, some of the most energetic explosions are happening right in our own celestial neighborhood on the surface of our parent star. Solar flares represent a more intimate and immediate form of cosmic violence, a constant reminder that our sun is not the serene, unchanging orb it appears to be, but a dynamic and occasionally volatile sphere of magnetized plasma. These are not the final death throes of a star, but rather powerful hiccups in its magnetic personality, eruptions that nonetheless pack a punch of almost unimaginable scale. A single, large solar flare is a tremendous explosion emanating from the sun's surface, a localized conflagration that can, in mere minutes, release energy equivalent to millions of powerful volcanic eruptions happening simultaneously. The engine behind this fury is the sun's incredibly complex and tangled magnetic field. Our star is not a solid body. It rotates differentially, meaning the equator spins faster than the poles. This differential rotation twists and stretches the magnetic field lines that are rooted deep within the solar interior, much like twisting a rubber band until it is taut with potential energy. These magnetic fields can arc through the sun's atmosphere, the corona, creating vast, dark structures we see as sunspots. In the intensely hot and chaotic plasma of the corona, these magnetic field lines can suddenly and violently reconfigure themselves in a process called magnetic reconnection. Picture two powerful magnetic loops snapping and crossing, forcing their fields to merge and realign. This sudden rearrangement releases a colossal amount of stored magnetic energy, which is then dumped into accelerating charged particles, mostly electrons and protons, to nearly the speed of light and heating the local plasma to tens of millions of degrees. The flash of light and radiation we observe as a solar flare is the direct result of this explosive magnetic energy release. To quantify the power of these events, scientists classify solar flares based on their peak X-ray brightness. The scale runs through the letters C, M, and X, with each letter representing a tenfold increase in energy output. A C-class flare is minor with few noticeable consequences. An M-class flare is moderate and can cause brief radio blackouts in the polar regions and minor radiation storms. But it is the X-class flare that is the true solar heavyweight. The largest X-class flares ever recorded have been calculated to release energy equivalent to billions of hydrogen bombs, or about 1/6 of the total energy the sun radiates every second. This is an amount of energy that is difficult to even conceptualize, all focused into a relatively small region of the solar surface and unleashed in a furious burst that can last from a few minutes to several hours. The effects of this explosive energy are not confined to the sun. While the initial flash of extreme ultraviolet and X-ray radiation travels to Earth at the speed of light, taking just over 8 minutes to arrive, the event often has a second, more impactful act. Many powerful flares are accompanied by what is known as a coronal mass ejection, or CME. This is a massive bubble of billions of tons of solar plasma, threaded with magnetic field lines, that is blasted away from the sun at speeds ranging from a few hundred to over 2,000 kilometers per second. It is this cloud of charged particles traveling through interplanetary space that interacts directly with Earth's magnetic field, creating the potential for both mesmerizing beauty and significant disruption. When the charged particles from a CME are funneled by Earth's magnetic field toward the poles, they collide with atoms of oxygen and nitrogen in the upper atmosphere, causing them to glow in the spectacular, shimmering curtains of light we know as the aurora borealis and aurora australis. This is the sun's most beautiful gift. However, the same geomagnetic storm that creates the auroras can also induce powerful electrical currents in long conductors on Earth, such as power grids and pipelines. The most famous example of this disruptive power was the Carrington event of 1859, a solar storm so powerful that telegraph systems across Europe and North America failed, with operators receiving shocks and some lines catching fire from the induced currents. In our modern, technologically dependent world, a similar event today could cause widespread and long-lasting power outages, disrupt satellite communications and GPS navigation, and pose a radiation risk to astronauts and airline passengers on polar routes. So, while solar flares are a testament to the dynamic nature of our star, they also serve as a powerful reminder of our vulnerability to the space weather generated by the most energetic explosions happening on our cosmic doorstep. While a solar flare is a brilliant flash of radiation signaling a sudden release of magnetic energy, it can often be the opening act for a far more physically substantial event, the coronal mass ejection. Think of the flare as the lightning bolt, an intense, localized burst of light and energy. The coronal mass ejection, or CME, is the thunder that follows, a colossal, slow-moving shockwave of actual solar material that carries the real potential for planetary impact. These are not mere bursts of light, but billion-ton projectiles of plasma, superheated gas composed of protons, electrons, and magnetic fields being violently hurled away from the Sun's outer atmosphere, the corona. The scale of a typical CME is almost beyond human comprehension. A single one can contain up to 1 billion tons of solar material, a mass equivalent to a large mountain, all heated to millions of degrees and expanding into a cloud that can be larger than the Sun itself. This immense structure is propelled outward at staggering speeds, ranging from a relatively sedate 250,000 miles per hour to a truly terrifying speed of over 5 million miles per hour for the most extreme events. Despite these incredible velocities, this is where a crucial distinction lies for us on Earth. The initial flash of a solar flare's X-rays and ultraviolet light reaches us in just over 8 minutes. A CME, being a massive cloud of physical particles, takes far longer to travel than 93 million miles from the Sun to Earth. This journey can take anywhere from half a day to 3 or 4 days, providing a critical window for warning and preparation that a flare simply does not offer. The connection between flares and CMEs is complex and fascinating. They are like siblings born from the same parent process of magnetic reconnection in the Sun's tangled magnetic field, but they are not inseparable. Powerful X-class flares are often accompanied by a CME, as the massive restructuring of magnetic fields literally blows a giant bubble of plasma loose from the Sun's gravitational grip. However, it is entirely possible for a significant CME to occur with only a minor or even no detectable flare. Conversely, some strong flares happen without launching any major mass ejection at all. This tells astronomers that while related, the mechanisms that produce the intense radiation of a flare and the bulk kinetic ejection of a CME are distinct processes, both stemming from the immense stresses built up in the Sun's dynamic atmosphere. The true significance of a coronal mass ejection is revealed when its path intersects with a planet like our own. When this billion-ton cloud of magnetized plasma slams into Earth's protective magnetic bubble, the magnetosphere, it doesn't simply bounce off. The impact compresses the magnetosphere on the day side and stretches it out on the night side into a long tail, transferring enormous energy into our near-space environment. This triggers a geomagnetic storm, a global disturbance of Earth's magnetic field. The most visible and beautiful effect of this storm is the aurora, as the solar particles are funneled toward the poles and ignite the atmosphere in dazzling displays of light that can sometimes be seen at much lower latitudes than usual. But the powerful electrical currents generated in our planet's magnetosphere and ionosphere during a severe geomagnetic storm have a more ominous side. These currents seek the path of least resistance, which can often be through human-made conductors on the ground. Long power lines, oil and gas pipelines, and undersea communication cables can all act as antennas, picking up these geologically induced currents. This can overload electrical grids, leading to widespread blackouts and potentially causing permanent damage to multi-million-dollar transformers that can take months or years to replace. Satellite operations are also severely affected, with increased drag in the swollen upper atmosphere altering orbits and intense radiation damaging sensitive electronics, disrupting global communications, navigation, and weather monitoring. The most famous historical example, the Carrington event of 1859, caused telegraph systems, the advanced technology of the day, to fail spectacularly, with operators receiving shocks and papers catching fire from the induced currents. A storm of similar magnitude today, in our far more electrically dependent world, could cause trillions of dollars in damage and take years to recover from, underscoring that the sun's most energetic explosions are not just distant curiosities, but events with direct and profound consequences for our technological civilization. To truly appreciate the raw power our sun can unleash, we need only look back to a specific week in the late summer of 1859. This was the week when solar violence reached down and touched the Earth in a way that was both spectacular and terrifying, an event now known as the Carrington event, named for the British astronomer Richard Carrington, who witnessed its birth. On the morning of September 1st, Carrington was sketching a group of large sunspots when he saw something unprecedented. Two brilliant beads of blinding white light suddenly appear over the sunspots, intensify, and then vanish within 5 minutes. Unbeknownst to him, he had just become the first human to witness and document the visual signature of a massive solar flare, but the flare was merely the starting pistol. The true event, a coronal mass ejection of almost unimaginable scale, was already racing toward Earth. The effects began less than 18 hours later, a remarkably short travel time that indicates the CME was ejected at an extraordinary speed. In the early hours of September 2nd, the night sky across the globe erupted in a fiery display of auroras. But these were not the familiar, gentle curtains of light typically confined to the polar regions. These auroras were so intense and widespread that they were seen as far south as the Caribbean, Colombia, and even Hawaii. Newspapers from the time report skies turning a bloody crimson, with light so brilliant that people could read newspapers by it in the middle of the night. Gold miners in the Rocky Mountains, thinking the glow was sunrise, began making breakfast at 1 in the morning. It was a global celestial light show of breathtaking beauty, but it was the harbinger of an invisible, destructive force. That force manifested most dramatically in the most advanced technology of the era, the worldwide telegraph network. As the geomagnetic storm intensified, it induced powerful electrical currents in the telegraph wires. Systems across Europe and North America catastrophically failed. Telegraph pylons threw sparks, operators received painful electric shocks, papers in telegraph offices caught fire. Perhaps most astonishingly, some operators found they could disconnect their batteries and still send messages, powered solely by the currents induced in the lines by the aurora-filled sky. The world's first electronic communication network was effectively fried by a storm that had begun 93 million miles away. The Carrington event serves as a stark historical case study, a direct demonstration of how solar activity can have direct and dramatic consequences for human technology. Now consider what a Carrington-level event would mean for our world today. The telegraph system of the 1800s was a simple, low-power, and largely isolated network. Our modern technological infrastructure is immeasurably more complex, interconnected, and vulnerable. A similar solar superstorm today would unleash a cascade of failures with potentially devastating consequences. The initial impact would induce powerful, fluctuating electrical currents in the ground over entire continents. These currents would seek the path of least resistance, which would be the continent spanning high-voltage transformers that form the backbone of our national power grids. These transformers are not designed to handle this kind of direct current geomagnetically induced current, or GIC. They would overheat and likely suffer irreversible damage. The result would not be a simple temporary blackout. It would be a catastrophic, long-term collapse of the electrical grid across vast regions, potentially plunging entire nations into darkness. The domino effect would be swift and severe. Without power, water treatment and distribution systems would fail within hours. Fuel pumps at gas stations would stop working, crippling transportation. Refrigeration would be lost, leading to the rapid spoilage of food. Banking and financial systems, which rely on continuous electricity and digital networks, would cease to function. Communication networks, cell towers, internet infrastructure, and satellites would be severely compromised or destroyed, isolating communities and crippling emergency response. The loss of electrical power would also mean the loss of heating and air conditioning, creating a public health crisis. The societal impact would be profound, and the recovery time for replacing massive, custom-built power transformers could stretch into years, not weeks or months. A modern Carrington event would be a global catastrophe on a scale never before experienced, a stark reminder that our technological civilization, for all its advances, exists at the mercy of our star's occasional fury. But beyond the explosive deaths of stars and the collisions of dense stellar corpses lies a different kind of cataclysm, one where the star is not the instigator of the violence but an innocent victim. This is the tidal disruption event, a cosmic disaster that unfolds when a star has the profound misfortune of wandering too close to the gravitational abyss of a supermassive black hole. These events are not powered by internal stellar processes, but by the sheer, overwhelming gravitational force of the universe's most enigmatic objects. A supermassive black hole, which can weigh millions or even billions of times more than our Sun, resides at the center of most large galaxies, including our own Milky Way. Normally, it lurks in darkness, but if a star ventures within its sphere of influence, it can trigger a spectacular and deadly light show. The star's doom begins with the black hole's tidal forces. Gravity weakens with distance, so the side of the star closest to the black hole feels a much stronger pull than the side farthest away. This difference in gravitational pull, known as a tidal force, is the same phenomenon that causes ocean tides on Earth due to the Moon's gravity, but on an astronomically more violent scale. As the star approaches, this tidal force overwhelms the star's own gravity, the force that holds it together as a coherent sphere. The star is literally stretched horizontally and compressed vertically, a process so dramatic that astronomers have given it the memorable, if unsettling, name of spaghettification. Over the course of just a few hours, the star is pulled apart into a long, thin stream of gas, like a piece of cosmic taffy. This stream of stellar debris doesn't just vanish into the black hole immediately. Instead, it follows complex orbits, with about half of the material being ejected away into the depths of space forever. The other half forms a swirling, chaotic accretion disk around the black hole. As this gas spirals inward, it is compressed and heated through friction and shocks to temperatures of millions of degrees. This superheated plasma then radiates a tremendous amount of energy, primarily in the form of ultraviolet and X-ray light, creating a brilliant flare that can outshine all the stars in the black hole's host galaxy combined for a period of several months to a year. This flare is the tidal disruption event's signature, a temporary beacon signaling the death of a star and a fleeting feast for a hidden supermassive black hole. What makes these events so fascinating to astronomers is that they act as natural experiments in extreme gravity. By studying the light curve and spectrum of the flare, scientists can measure the mass of the central black hole and understand the physics of how matter behaves just outside the event horizon. Each tidal disruption event is a unique probe, revealing the properties of otherwise dormant black holes and providing crucial insights into the fundamental laws that govern the most intense gravitational environments in the universe. Just as no two stars are exactly alike, neither are their demises when they fall victim to a black hole. The tidal disruption event is not a one-size-fits-all catastrophe. It comes in a surprising variety of flavors, each producing a unique observational signature that astronomers must learn to decipher. The character of the resulting cosmic flare depends heavily on two key factors: the nature of the star being destroyed and our particular line of sight to the event. Think of it like a car crash. The outcome varies dramatically depending on whether the vehicle is a compact car or a massive truck, and what angle you're viewing the collision from. First, consider the star itself. The most common victim is a star similar to our Sun, a so-called main sequence star. When a star like this is torn apart, its debris forms an accretion disk that shines brilliantly across many wavelengths. However, if the unlucky star is a red giant, a much larger, more diffuse star in the final stages of its life, the disruption plays out very differently. A red giant is so large that it can actually be torn apart before it even gets close enough to the black hole to be fully captured. This partial disruption can lead to a series of smaller, repeated flares as the star loses layers over multiple orbits, rather than a single cataclysmic event. Furthermore, the composition of the star matters. A helium-rich star, or one with unusual elemental abundances, will produce a light show with distinct chemical fingerprints, allowing scientists to perform a kind of cosmic autopsy on the victim long after it has been consumed. The second crucial ingredient is perspective, our viewing angle relative to the accretion disk and the jet of material that might be launched. If we are fortunate enough to be looking almost directly down the barrel of a relativistic jet launched during the disruption, we might witness an extremely luminous and rare event known as a jetted tidal disruption event. This is akin to seeing a focused blowtorch pointed straight at us, amplifying the brightness tremendously. More commonly, we see these events from a more oblique angle, where the glow of the accretion disk itself dominates the emission. This can lead to a different distribution of light, with some events appearing brightest in high-energy X-rays generated close to the black hole, while others shine more intensely in ultraviolet or even visible light from the outer, cooler parts of the debris stream. This diversity makes tidal disruption events both a challenge and a treasure trove. An event that flares brightly in optical light but is faint in X-rays tells a different story about the structure of the debris disk and the black hole's feeding habits than one that is an X-ray powerhouse. By collecting observations across the entire electromagnetic spectrum, from radio waves to gamma rays, astronomers can piece together a three-dimensional picture of the destruction. Each new tidal disruption event discovered is like adding another piece to a complex puzzle, helping to build a more complete understanding of how black holes interact with their environments and how the fundamental laws of physics operate under the most extreme conditions imaginable. But while we've seen how the collision of neutron stars can create cosmic fireworks, the story of these stellar corpses is far from over. Some neutron stars are born with a truly terrifying secret, a hidden power that makes them the most volatile and magnetic objects in the known universe. These are the magnetars, and if a typical neutron star is a city-sized diamond, a magnetar is that same diamond spinning at a furious rate and wrapped in coils of the most powerful magnets imaginable. Their defining feature is a magnetic field of almost incomprehensible strength. To put it in perspective, the magnetic field on Earth is strong enough to guide a compass needle. The magnetic field of a typical neutron star is 1 trillion times stronger than that, but a magnetar's field is another 1,000 times more intense yet, reaching levels of 1 quadrillion times Earth's magnetic field. This is a level of power that literally warps the very fabric of reality around it. The sheer intensity of this magnetic field creates an environment that defies physics as we know it. If you were to venture within about 600 miles of a magnetar, a distance roughly from New York to Cleveland, the magnetic field would become a lethal force. It would be so powerful that it wouldn't just affect your body, it would fundamentally alter the nature of matter itself. The field would strip the atoms that compose you down to a cigar-shaped, ionized plasma, warping their electron clouds into strange, needle-like shapes. But the real violence occurs on the surface of the magnetar itself. This immense magnetic stress is constantly acting on the star's solid, immensely strong crust, a crystalline surface harder than diamond. The magnetic fields are under such incredible strain that they writhe and twist, putting unbearable pressure on the crust until it can no longer hold. The crust suddenly and violently cracks, much like the tectonic plates on Earth, but with energy releases that are galactic in scale. These cosmic fractures are known as starquakes, and they are among the most energetic seismic events in the cosmos. When a magnetar's crust snaps, it releases a colossal amount of pent-up magnetic energy in a matter of seconds. The result is a giant flare, an eruption of gamma rays and X-rays so intense that for a fleeting moment, it can outshine every other source of high-energy light in our entire galaxy, including the combined output of hundreds of billions of stars. The energy released in one of these flares is staggering. In a tenth of a second, a magnetar can unleash more energy than our sun emits in 100,000 years. The most famous example occurred in 2004 when a magnetar named SGR 1826, located about 50,000 light-years away in the constellation Sagittarius, experienced a starquake. The flash of gamma rays was so powerful that it actually compressed Earth's upper atmosphere, despite being halfway across the galaxy, and temporarily ionized a layer that reflects long-range radio signals. For a fraction of a second, this single, tiny star 20 kilometers across was brighter than the full moon, but in the lethal language of gamma rays. These magnetar flares are a stark reminder that even in death, a star can possess a temper of truly cosmic proportions. The idea that a tiny, distant object could reach out and physically touch our planet from halfway across the galaxy sounds like science fiction. But on December 27, 2004, that's exactly what happened. It was on that day that a magnetar known as SGR 180620, located an incredible 50,000 light-years away in the constellation Sagittarius, decided to announce its presence in the most dramatic way imaginable. For a fifth of a second, this city-sized stellar corpse released a flare of gamma-ray energy so immense that it temporarily became the brightest object ever detected outside our solar system, outshining the full moon in gamma rays and delivering a palpable jolt to our entire planet. The sheer scale of the energy release is almost impossible to overstate. In that brief flicker of time, the magnetar unleashed more energy than our sun has emitted over the last 250,000 years. All of that power was concentrated into a single, focused burst. When that pulse of high-energy radiation finally reached Earth after its 50,000-year journey, it did something no astronomical event had ever been observed to do before. It physically altered our planet's environment. The gamma rays slammed into the upper layers of our atmosphere, violently ionizing atoms and molecules. This sudden influx of charged particles caused a measurable, instantaneous compression of Earth's protective magnetic shield, the magnetosphere. For a moment, the very bubble that safeguards us from the solar wind was pushed inward by the force of the blast. The effects were detected by a fleet of satellites, including the International Space Station, which registered a powerful surge of radiation that temporarily blinded the sensors on several spacecraft. More remarkably, the pulse was strong enough to be reflected off the moon, and radio astronomers detected its echo from the lunar surface. Down on Earth, the ionization of the upper atmosphere had a direct, though subtle, impact on long-range radio communications, causing a brief but notable disturbance. This was not a life-threatening event for us on the surface. Our thick atmosphere absorbed the radiation. But for any astronauts in space or any electronic systems in orbit, it was a stark reminder of the vulnerability of technology to cosmic violence. What makes the 2004 event so uniquely significant is the distance involved. 50,000 light-years is not a trivial journey. It means the explosion occurred halfway across our own Milky Way galaxy. For a signal to remain so powerful after traveling across such an immense void speaks to an almost unimaginable power source. Astronomers calculated that if this magnetar had been located not 50,000 light-years away, but as close as 10 light-years, a mere stone's throw in galactic terms, the effects would have been catastrophic. The gamma-ray blast would have severely depleted our ozone layer, potentially triggering a mass extinction event on par with the asteroid impact that wiped out the dinosaurs. The SGR 1806-20 flare stands as a permanent benchmark, a definitive demonstration that the universe harbors forces capable of reaching across the vast emptiness of space and reminding us that we are not isolated observers, but active participants in a dynamic and occasionally dangerous cosmos. But what happens when the destructive power we've been exploring isn't a brief, violent flash, but a continuous, billion-year-long eruption on a scale that dwarfs even the mightiest supernova? To find the answer, we must zoom out from individual stars and look at the hearts of entire galaxies. Here, we encounter a phenomenon that redefines the very concept of an explosion, the active galactic nucleus, or a GN. This is the intensely bright, energetic core of a galaxy, and its power source is a supermassive black hole that is actively feeding, turning the process of accretion into a sustained, cosmic-level detonation. At the center of this maelstrom lies a gravitational monster, a black hole with a mass millions or even billions of times greater than our Sun. But unlike the quiet, dormant black holes we might imagine, the one in a GN is a voracious consumer. It is surrounded by a vast, swirling whirlpool of gas, dust, and even entire stars that have wandered too close. This structure, known as an accretion disk, is the engine of the explosion. As material spirals inward at velocities approaching the speed of light, it is compressed and heated by immense frictional forces to temperatures of millions of degrees. In this superheated state, the matter glows with a blinding intensity across the entire electromagnetic spectrum, from radio waves to gamma rays. The energy released in this process is so colossal that the tiny central region of the galaxy, the active nucleus, can outshine the combined light of every single one of the galaxy's hundreds of billions of stars. We are no longer talking about a star outshining its galaxy for a few weeks. We are talking about a pinpoint of light that dominates its entire cosmic city for eons. This continuous explosion often produces the most spectacular structures in the universe, colossal jets that can stretch for millions of light years. Physics is similar to what we see in microquasars and gamma-ray bursts, but scaled up to an almost unimaginable degree. The intense magnetic fields and rapid rotation of the accretion disk funnel some of the infalling material into two narrow, oppositely directed beams that are launched perpendicular to the disk at nearly the speed of light. These jets, composed of charged particles and magnetic fields, plow through the intergalactic medium, creating immense lobes that radiate powerfully in radio wavelengths. When one of these jets is pointed almost directly at Earth, we see an especially bright and variable type of a GN called a blazar. From our perspective, the effects of relativity boost the jet's light, making it appear even more brilliant and giving us a front-row seat to the raw power erupting from the galactic core. The scale of an GN is a true testament to the universe's capacity for sustained violence. While a supernova is a spectacular finale, an active galactic nucleus is a constant state of controlled chaos, a billion-year-long fireworks display where the gravitational energy of a supermassive black hole is converted into a beacon of light that can be seen across the cosmos. These engines not only shape the evolution of their host galaxies by heating surrounding gas and suppressing star formation, but they also serve as the ultimate laboratories for testing physics under the most extreme conditions, proving that the universe's most energetic explosions are not always fleeting events, but can also be enduring monuments to power. Now, having explored the immense, sustained fury of an active galactic nucleus, we come to a special case where our cosmic perspective turns a fascinating phenomenon into an absolutely dazzling one. When the universe lines things up just right, and one of those relativistic jets from an AGN is aimed almost directly at our solar system, we don't just see a bright galaxy, we witness a blazar. The term blazar might sound like something from science fiction, but it describes one of the most energetic and variable classes of objects in the entire known universe. It all comes down to a simple but profound matter of geometry and relativity. An active galactic nucleus is already brilliant, but its light is spread out in many directions. A blazar, however, funnels a colossal fraction of its total energy into a beam pointed right at us, like staring directly into the beam of the most powerful lighthouse in the cosmos. This alignment has dramatic consequences for how we perceive these objects. Because the jet is composed of material moving at over 99.9% the speed of light, strange effects from Einstein's theory of special relativity come into play. The light and other radiation emitted by the jet get a massive boost in energy and intensity, an effect known as relativistic beaming. This makes the blazar appear hundreds or even thousands of times brighter than it would if the jet were pointing in any other direction. Furthermore, this beaming effect compresses the timescale of the variations we see. The blazar's brightness doesn't just change over years or months, it can flare up dramatically in a matter of hours, days, or even minutes. This incredible variability is a hallmark of the blazar phenomenon, a sign that we are witnessing processes occurring in a very small, violent region near the supermassive black hole, with changes amplified by the jet's headlong rush toward us. The energy output of a blazar is so comprehensive that it truly earns the title of a multi-messenger source. We detect their signal across the entire electromagnetic spectrum, from long wavelength radio waves all the way up to the most energetic gamma rays. In fact, blazars are dominant figures in the gamma-ray sky, as seen by space telescopes like Fermi. The processes that generate this light are complex and layered. The radio emission typically comes from the outer, more extended parts of the jet, where electrons spiraling around magnetic field lines produce synchrotron radiation. As we move to higher energies, infrared, optical, and ultraviolet, we are seeing this same synchrotron process from more energetic electrons closer to the base of the jet. But the story doesn't stop there. The most energetic gamma rays are thought to be produced when these same high-speed electrons collide with lower-energy photons, either from the synchrotron process itself or from the intense light of the accretion disk, boosting them up to gamma-ray energies in a process called inverse Compton scattering. By studying the unique signature of a blazar's light across all these wavelengths, astronomers can map out the structure of the jet and understand the frenetic particle acceleration happening within it. What makes blazars particularly important to astronomers is that they are more than just cosmic curiosities. They are natural particle accelerators of unbelievable power, far exceeding anything we can build on Earth. The jets act as vast, natural laboratories where conditions exist that we can only dream of replicating. By observing how blazars behave, we gain crucial insights into the physics of relativistic jets, the behavior of matter and magnetic fields in extreme gravity, and the mechanisms that can accelerate particles to within a whisper of the speed of light. Every time a blazar flares, it sends us a data-rich message from the immediate vicinity of a supermassive black hole, offering a unique window into the most energetic and persistent engines in the universe. If the sustained brilliance of an active galactic nucleus gives us a window into galactic powerhouses, then quasars are that same phenomenon pushed to its ultimate extreme, acting as cosmic lighthouses whose beams have been traveling across space for a significant fraction of the universe's entire history. The name quasar is a shortening of quasi-stellar radio source, a label given in the 1960s when these objects appeared as star-like points of light in optical telescopes but emitted bizarre and powerful radio signals. We now understand that a quasar is not a star at all, but the intensely bright active nucleus of a very distant galaxy, powered by a supermassive black hole that is feeding at a ferocious rate. What makes them truly special, however, is their role as time machines. The light from the quasars we study today has been journeying for billions of years, meaning we are not seeing them as they are now, but as they were when the universe was young, hot, and dense. The incredible distances involved are key to their brilliance and their importance, because the expansion of the universe stretches the wavelength of light traveling through it. A phenomenon known as redshift, the light from extremely distant objects is shifted toward the red end of the spectrum. The greater the redshift, the farther away the object and the further back in time we are looking. Quasars hold the record for some of the highest redshifts ever measured, with their light revealing a universe that was only 700 or 800 million years old, a mere infant compared to its current age of 13.8 billion years. To be visible across such a vast gulf of space, these objects must be phenomenally luminous, often outshining their entire host galaxies by a factor of 1,000. This tells us that the black holes at their hearts were not just massive, they were already monsters weighing billions of suns when the cosmos was in its relative infancy, a fact that challenges our models of how such behemoths could form and grow so quickly. Studying the light from these ancient beacons provides a direct probe into the conditions of the early universe. As a quasar's light travels toward Earth, it passes through vast clouds of gas that lie between galaxies, known as the intergalactic medium. Different elements in these clouds absorb specific wavelengths of the quasar's light, creating a unique barcode of dark lines in the quasar's spectrum. By analyzing this Lyman alpha forest, astronomers can piece together a history of the universe's chemical composition and structure over billions of years. It's like analyzing the spectrum of a distant lighthouse through a thick cosmic fog. The patterns in the light tell us not only about the lighthouse itself, but also about the composition and density of the fog it traveled through. This allows scientists to map the large-scale structure of the cosmos and understand how it evolved from a nearly smooth distribution of matter after the Big Bang into the intricate cosmic web of filaments and voids we see today. Furthermore, quasars are crucial laboratories for understanding the life cycle of supermassive black holes. The very existence of these brilliant objects in the early universe suggests that black holes underwent a period of extremely rapid growth, gorging on immense amounts of gas and dust. This frenzied feeding would have been fueled by the frequent mergers of young, gas-rich galaxies, a common occurrence in the crowded early cosmos. By measuring the masses of these ancient black holes, deduced from the speed of gas whirling around them, and comparing them to their modern-day counterparts, astronomers can trace the co-evolution of black holes and their host galaxies. It appears that the most active quasar phase represents a key period of growth, after which the black hole's own energy output, in the form of powerful jets and radiation, eventually blows away the surrounding gas, shutting off its own food supply and transitioning into a quieter, dormant state like the black hole at the center of our own Milky Way. In this way, each quasar we observe is a frozen snapshot of a universal youth, a brief but brilliant era of black hole adolescence that helped shape the galaxies we see around us today. These spectacular explosions we've been exploring are far more than just isolated cosmic fireworks. They are fundamental architects shaping the very structure and destiny of galaxies over billions of years. It's a beautiful paradox where the most violent acts of destruction are, in fact, essential creative processes on the grandest of scales. The cycle begins with the death of massive stars. When a supernova detonates, its immense shockwave doesn't just scatter newly forged elements, it also acts as a colossal cosmic snowplow racing through the surrounding interstellar medium. As this spherical wall of energy expands, it slams into colder, quieter clouds of hydrogen gas. The force of the impact is tremendous, violently compressing the gas and increasing its density. In the cold, dense heart of these compressed regions, the relentless pull of gravity can finally overcome the internal gas pressure that was resisting collapse. This gravitational collapse is the very seed of star birth. The supernova's destructive shockwave, therefore, becomes the trigger for the creation of a new generation of stars. Our own solar system is thought to have formed from a cloud of gas that was enriched and likely compressed by the debris of one or more ancestral supernova, making these explosions not just creators of elements, but also the midwives for new stellar nurseries and their planetary systems. This creative influence, however, is balanced by an equally powerful regulatory force emanating from the very hearts of galaxies. While supernova work on a local, stellar neighborhood scale, active galactic nuclei exert a global influence that can dictate the entire life cycle of their host galaxy. Recall that an AGN is powered by a supermassive black hole feasting on surrounding material, often launching jets and driving powerful winds of hot gas outward. These outflows are not gentle breezes. They are hurricane-force winds that carry an incredible amount of energy and rage across the galaxy for thousands of light years. When this torrent of energy slams into the galaxy's reservoirs of cold gas, the very raw material needed to form new stars, it has a dramatic effect. The cold gas is violently heated to extreme temperatures, making it much more difficult for it to cool down, condense, and collapse into new stars. In more extreme cases, the outflow can be so powerful that it doesn't just heat the gas. It blows it completely out of the galaxy, ejecting the potential for future star formation into the vast intergalactic void. This process, known as galactic feedback, is now understood to be a critical mechanism that prevents galaxies from growing uncontrollably. Without this regulating influence, a large galaxy would continue to convert its cold gas into stars until it exhausted its fuel supply, potentially resulting in a much larger, bluer, and more chaotic stellar system. The AGN, by heating and expelling gas, effectively puts a brake on star formation. It's a cosmic thermostat. When the black hole feeds vigorously, it becomes active, and its energetic output stifles the growth of new stars, ensuring the galaxy evolves in a more orderly fashion. This feedback loop is a key reason why we see the galaxy types we do today, from the gas poor, red and dead, elliptical galaxies where star formation has been quenched, to the more sedate spiral galaxies like our Milky Way. The most energetic explosions in the universe, from the death cries of stars to the sustained fury of galactic cores, are therefore the master sculptors of the cosmic landscape, carving out the shapes, sizes, and destinies of the galaxies that form the visible backbone of our universe. While the brilliant flash of a supernova captures our attention, it sends out another, more stealthy form of energy that permeates the cosmos: cosmic rays. These are not rays of light, but a relentless drizzle of high-energy atomic fragments, mostly protons, with a mix of helium nuclei and heavier elements racing through the void at nearly the speed of light. This is the invisible shrapnel from cosmic explosions, a form of radiation so pervasive that trillions of these particles are passing through your body every single second, completely unnoticed. They are the silent, energetic ghosts of stellar cataclysms, and for over a century their origin has been one of astronomy's most compelling puzzles. The mystery began in the early 1900s when scientists noticed that electroscopes, instruments used to detect electric charge, would slowly discharge even when perfectly insulated. The only explanation was that some form of highly penetrating radiation was constantly ionizing the air, and it was coming not from the ground but from space. We now know this radiation is the cosmic ray background, but how do atoms, even single protons, get accelerated to such fantastic energies? The leading theory points directly to the supernova remnants we discussed earlier. Think of the expanding shockwave from a stellar explosion as a colossal, natural particle accelerator. As this spherical wall of energy plows through the interstellar medium, it creates a turbulent region of powerful magnetic fields. A charged particle, like a proton, can get caught in this magnetic maelstrom, bouncing back and forth across the shock front. With each crossing, it gains a little more speed, much like a surfer being pushed repeatedly by a wave. Over time, this process, known as Fermi acceleration, can whip these particles up to energies far beyond anything achievable in human-built particle colliders like the Large Hadron Collider. These cosmic rays then travel for millions of years, weaving their way through the magnetic fields that thread our galaxy. They are a crucial, though invisible, component of the galactic ecosystem. Their high energy makes them a significant source of ionization in cold, dark molecular clouds, the very nurseries where new stars are born. By influencing the chemistry and electrical properties of these clouds, cosmic rays may play a role in triggering the gravitational collapse that leads to star formation. Furthermore, when these high-energy particles collide with the nuclei of interstellar atoms, they can trigger nuclear reactions called spallation, which are responsible for creating a small but significant fraction of the lighter elements in the universe, such as lithium, beryllium, and boron. So, while supernovae forge the heavy elements, their cosmic ray byproducts help to synthesize the lighter ones, filling in the periodic table through a different kind of violent interaction. For us on Earth, this constant barrage has very real effects. Our planet's magnetic field and thick atmosphere provide a superb shield, deflecting most cosmic rays and absorbing their energy. But at high altitudes, the story changes. Airline crews and frequent flyers are exposed to higher levels of radiation from cosmic rays, a factor carefully monitored in aviation safety. For astronauts, especially those on missions outside the protective embrace of Earth's magnetosphere, cosmic rays pose a serious health risk. These high-energy particles can damage DNA and increase the long-term risk of cancer, making them one of the primary challenges for future long-duration missions to the Moon or Mars. Scientists are actively researching better shielding materials to protect explorers from this invisible rain, a direct example of how understanding these distant cosmic explosions is vital for our own ambitions in space. Every time a massive star dies, it not only seeds the galaxy with the elements for life, but also fills it with an energetic haze that subtly influences the chemistry of star birth and the practical realities of space travel, linking the grandest cosmic events directly to our own technological future. But how do we actually catch these elusive, high-energy particles to trace them back to their source? The challenge is immense. A cosmic ray proton arriving from deep space is invisible until it makes contact with our atmosphere. It's here, about 10 to 15 kilometers above the ground, that the real detective work begins. When one of these high-energy particles, carrying the energy of a well-hit tennis ball but concentrated into a single atomic nucleus, slams into the top of our atmosphere, it doesn't arrive quietly. It initiates an avalanche, a cascade of secondary particles known as an extensive air shower. The initial proton collides with a nucleus of nitrogen or oxygen, shattering it and creating a spray of pions, kaons, and other secondary particles. These, in turn, collide with other air molecules, creating a rapidly expanding, pancake-shaped front of billions of secondary particles, electrons, muons, and photons, all racing toward the ground at nearly the speed of light. By the time this particle front reaches the Earth's surface, it can spread over an area of more than 10 square miles. Detecting this faint, fleeting echo of a cosmic catastrophe requires an observatory of almost unimaginable scale. This is the precise mission of the Pierre Auger Observatory, a breathtaking feat of international scientific collaboration located on the vast Pampa Amarilla in western Argentina. The scale of this facility is difficult to grasp. It covers an area of over 3,000 square kilometers, making it roughly the size of Rhode Island. Instead of a single giant telescope, the observatory is a sprawling array of 1,600 individual detectors strategically spaced across the plains. Each detector is a cylindrical tank containing 12,000 liters of ultra-pure water, sealed in darkness. When the particles from an extensive air shower zip through this water, they travel faster than the speed of light in that medium, creating a faint blue glow of Cherenkov radiation, much like the sonic boom of a jet breaking the sound barrier but for light. An array of sensitive photomultiplier tubes lining the tanks captures this faint flash, recording its precise timing and intensity. But the Auger Observatory doesn't rely on a single technique. To get a complete picture of the air shower, it uses a hybrid detection system. Scattered across the array are 24 fluorescence telescopes that point their eyes toward the night sky. These don't look at stars, they look at the air itself. As the air shower develops, it excites nitrogen molecules in the atmosphere, causing them to fluoresce with a faint ultraviolet light. This allows scientists to essentially watch the shower develop in real time, like tracing the path of a lightning bolt across the sky. By combining the precise timing information from the ground array with the longitudinal profile of the shower from the fluorescence telescopes, researchers can reconstruct the energy, direction, and even the mass of the original cosmic ray particle with remarkable accuracy. It's a perfect marriage of two detection methods, turning a huge swath of the Argentine landscape into the world's most powerful cosmic ray camera. The ultimate goal of this immense effort is to solve the century-old mystery. Where do these ultra-high-energy cosmic rays come from? For the lower energy rays, the answer is somewhat clearer. They are likely accelerated by the shockwaves of supernova remnants within our own galaxy. But the particles with the very highest energies, carrying more than 10 to the 20th power electron volts, are a different story. They are so energetic that the Milky Way's magnetic field is too weak to contain them. They must be extragalactic in origin. The Auger Observatory has made significant progress in this hunt. While the trajectories of these particles are bent by intergalactic magnetic fields, making pinpointing their sources difficult, the data has revealed a tantalizing anisotropy, a statistical unevenness in their arrival directions. This pattern suggests they are not coming from all points equally, but seem to be correlated with the distribution of matter in the nearby universe. The prime suspects for their accelerators are the most energetic environments we know, active galactic nuclei, where the powerful jets from supermassive black holes could act as natural particle accelerators on a galactic scale, or perhaps violent galaxy mergers and lobes of radio galaxies. Every time a tank in Argentina registers a flash of Cherenkov light, it's collecting a piece of evidence in a cosmic forensic investigation, tracing a piece of invisible shrapnel back to the universe's most powerful explosions, building a map of violence that stretches across the cosmos. For all our powerful telescopes and satellites, for centuries we have been deaf to the universe, only able to see its violent explosions. But in 2015, a new sense opened up, allowing us for the first time to literally hear the cosmos. This new sense listens not for light, but for the subtle vibrations in the very fabric of reality, the ripples in space-time known as gravitational waves. Albert Einstein predicted their existence a century ago as a consequence of his general theory of relativity, envisioning that the most violent motions of massive objects would send waves of distortion radiating outward at the speed of light, stretching and squeezing space itself as they passed by. For decades, this was considered an untestable theoretical curiosity. The distortions were thought to be so incredibly tiny that detecting them seemed an impossible dream. That dream became a reality on September 14, 2015, when the twin observatories of the Laser Interferometer Gravitational Wave Observatory, or LIGO, caught a signal that would change astronomy forever. The signal was a perfect match for Einstein's predictions, a rapid chirp that increased in both frequency and amplitude, culminating in a final, definitive ring-down. The source was the collision and merger of two black holes, one about 36 times the mass of our Sun, the other 29, located over 1 billion light-years away. In the final fraction of a second before they merged, these unimaginably dense objects whipped around each other hundreds of times per second, pumping tremendous energy into the gravitational waves that eventually reached Earth. The detection was a triumph of human ingenuity, confirming a key part of Einstein's theory and, more importantly, opening an entirely new window on the universe. The technology that made this possible is a masterpiece of precision engineering. LIGO doesn't look like a traditional telescope. It consists of two immense L-shaped facilities in the United States, one in Washington State and the other in Louisiana, with arms 4 kilometers long. Inside each arm, a powerful laser beam is split and sent racing down two perpendicular vacuum tubes, reflected by mirrors and then recombined. In perfectly calm space, the light waves cancel each other out. But when a gravitational wave passes through, it minutely changes the length of the arms. One arm gets stretched while the other is squeezed, and then vice versa. This change is almost unbelievably small, a distortion of less than 1,000th the diameter of a proton. Yet LIGO exquisitely sensitive mirrors can detect this shift, causing the laser light to no longer cancel out perfectly and creating a measurable signal. By having two detectors separated by thousands of miles, scientists can confirm the signal is real and not a local disturbance like a passing truck or an earthquake, and they can triangulate the rough direction of the source on the sky. The sound of these events is as informative as their light. The signal from a black hole merger is a clean, pure tone, a rising chirp because as the black holes spiral closer, they orbit faster, increasing the frequency of the gravitational waves. But the most scientifically rich sound yet captured came on August 17, 2017, when LIGO and its European counterpart, Virgo, detected a very different signal. This one lasted for about 100 seconds, far longer than the black hole chirps, and it was followed just 2 seconds later by a gamma-ray burst detected by space telescopes. This was the sound of two neutron stars colliding. The longer duration indicated that these less massive, city-sized objects spiraled together for more orbits before merging, creating a more complex gravitational wave pattern. This event marked the dawn of multi-messenger astronomy, where the same cosmic catastrophe was observed through both gravitational waves and light, providing a complete picture of the explosion that forged heavy elements like gold and platinum. We are no longer just watching the silent movie of the cosmos. We have finally turned on the sound, listening to the low-frequency hum of black hole dances and the high-pitched crescendo of stellar collisions, hearing the universe speak in the language of spacetime itself. This new way of listening to the cosmos has fundamentally transformed our field of view, ushering in what scientists call the era of multi-messenger astronomy. For centuries, our understanding of the universe was built almost entirely on a single sense, sight. We collected photons, particles of light across the electromagnetic spectrum, from radio waves to visible light to gamma rays. But now, we are no longer just silent observers of a cosmic light show. We have gained new senses. We can feel the vibrations of spacetime through gravitational waves, and we can detect the ghostly passage of nearly massless particles called neutrinos. By combining these different messengers, we can construct a complete, multi-dimensional picture of a single cataclysmic event, much like combining the sound of a crash with the sight of broken glass to understand the full story of an accident. The power of this approach was demonstrated in a landmark event that will be remembered as a turning point in astronomical history. On August 17, 2017, the LIGO and Virgo gravitational wave observatories detected a signal unlike any they had seen before. It was not the brief, sharp chirp of merging black holes, but a longer, rising tone that lasted for approximately 100 seconds. This was the sound of two neutron stars, each more massive than our Sun, but only the size of a city, locked in a final, fatal spiral. The characteristics of the gravitational waves immediately told scientists this was a monumental discovery. Crucially, just 2 seconds after the gravitational wave signal peaked, NASA's Fermi Gamma Ray Space Telescope detected a short gamma-ray burst coming from the same general area of the sky. This 1-2 punch of gravitational waves and gamma rays was the trigger for an unprecedented global campaign. Within hours, astronomers around the world were pointing every available telescope toward the patch of sky identified by the combined data. The race was on to find the source, and they found it in a galaxy known as NGC 4993, about 130 million light-years away. There, they witnessed the magnificent glow of a kilonova, the visible and infrared afterglow of the neutron star collision. For days and weeks, they watched as this cosmic forge produced and scattered heavy elements like gold and platinum across space. This was multi-messenger astronomy in its purest form. The gravitational waves told us about the dynamics of the massive objects involved, their masses and how they merged. The gamma-ray burst revealed the intense, focused energy of the relativistic jets, and the light from the kilonova showed us the chemical aftermath, the creation of precious elements in real time. It was a single event narrated through 3 completely different languages, each providing a chapter of the story that the others could not. This collaborative detection solved multiple cosmic mysteries at once. It confirmed with direct evidence that short gamma-ray bursts are indeed caused by neutron star mergers. It provided the first direct observation of the site where the R process, the rapid neutron capture process, creates the heaviest elements in the universe. And it provided a new, independent way to measure the expansion rate of the universe by comparing the distance inferred from the gravitational waves to the redshift of the host galaxy. The success of this single observation has cemented multi-messenger astronomy as the future of cosmic exploration. We are no longer just watching the universe, we are feeling its vibrations and catching its particles, assembling a richer, more complete symphony of the cosmos than we ever thought possible. And just when we thought we had catalogued the universe's most extreme explosions, the cosmos unveils a new mystery, one that is both incredibly brief and bafflingly powerful. Imagine a flash of radio waves so short it would be over in the blink of an eye. A burst of energy that can outshine an entire galaxy for just a few milliseconds and then vanish without a trace. This is the enigma of fast radio bursts, or FRB, a phenomenon so new that the first one wasn't discovered until 2007, hidden in archival data from a radio telescope in Australia. Their defining characteristic is their breathtaking speed. While a gamma-ray burst lasts for seconds or minutes, an FRB is typically all over in less than 1,000th of a second. In that fleeting instant, however, it can release as much energy as our Sun puts out over several decades. The mystery of FRBs is layered. For years after their discovery, they were solitary events, a single, brilliant pop of radio static from a random point in the sky, never to be heard from again. These one-off bursts suggested a catastrophic, self-destructing source. But then, in 2016, everything changed. Astronomers discovered an FRB that repeated. It wasn't a single cataclysm. It was an object that could fire off multiple bursts, sometimes sporadically, sometimes in frantic clusters. This single finding split the FRB field in two, suggesting there might be at least 2 different types of sources. One that produces a single, immensely powerful final explosion, and another that can somehow survive its own violent outbursts and produce more. The repeating bursts provided a crucial clue, as astronomers could now point telescopes at the same patch of sky and wait for the source to speak again, allowing them to triangulate its home galaxy, often billions of light-years away. So, what cosmic engine could possibly power such a fleeting yet immense release of energy? The leading suspect brings us back to an object we've already met, but in its most extreme form, the magnetar. You'll recall that a magnetar is a neutron star with a magnetic field so strong it can crack the star's crust, causing starquakes and giant flares. Theorists propose that an especially powerful starquake, or a sudden reconfiguration of the magnetar's immense magnetic field, could launch a shockwave through the magnetized plasma surrounding the star. As this shockwave plows outward, it could cause the plasma to emit an incredibly bright, coherent blast of radio waves. A fast radio burst. This model is particularly compelling because we have actually detected an FRB-like burst coming from a known magnetar within our own galaxy, providing the first direct link between a specific object and this mysterious phenomenon. But magnetars aren't the only candidates in this cosmic detective story. Other theories are equally fascinating. Some scientists suggest FRBs could be produced by the collision of incredibly dense objects, like neutron stars or even asteroid-sized chunks of strange matter hitting a neutron star's surface. Another exotic idea involves highly magnetized, rapidly spinning neutron stars that act like cosmic lighthouses, but whose beams are only visible as a brilliant flash if they happen to sweep across our line of sight under very specific conditions. The sheer diversity of the bursts, their durations, their energy, and whether they repeat strongly suggests that we may not be dealing with a single type of event, but a whole family of radio explosions, each with its own unique trigger. The study of FRBs is still in its thrilling infancy, a field where every new detection has the potential to overturn old ideas and open up entirely new chapters in our understanding of the universe's most transient and energetic signals. Theoretical models are one thing, but nothing compares to a direct, local observation to solve a cosmic mystery. For over a decade, the source of fast radio bursts was a puzzle with no clear picture on the box. Were they from distant galaxies or nearby? Were they one-off cataclysms or repeatable events? The breakthrough came not from the distant cosmos but from our own celestial backyard. In April 2020, a known magnetar within the Milky Way, named SGR 1935+215, suddenly went into an active phase. As astronomers monitored this stellar corpse, something extraordinary happened. It unleashed a brilliant millisecond burst of radio waves that was detected by the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, radio telescope. This was not just any radio burst. It had all the hallmark characteristics of a genuine fast radio burst, but its origin was unmistakable, a magnetar we had been watching for years. This detection was a watershed moment for astronomy. For the first time, we had a smoking gun, directly linking at least one class of FRBs to the violent activity of magnetars. The significance of this event cannot be overstated, because the burst came from a source inside our galaxy. Its distance was known, which allowed scientists to calculate its intrinsic energy with high precision. It turned out to be about 1,000 times less energetic than the extragalactic FRBs detected from billions of light-years away. This was a crucial piece of evidence. It demonstrated that the mind-bogglingly powerful FRBs we see from other galaxies are not necessarily caused by a different, more exotic process. They are simply the same magnetar-powered phenomenon, but seen from vastly greater distances. The magnetar in our galaxy provided a nearby, calibrated example of the engine, confirming that these ultramagnetic neutron stars are indeed capable of producing the specific, short-duration radio signals that had baffled scientists for so long. Yet, as often happens in science, answering one question immediately raised several more. The detection proved the who, but it left the how wide open. What specific physical process on a magnetar's surface can possibly generate such an intense, focused flash of radio waves in just a few milliseconds? The leading theory involves starquakes and sudden magnetic reconnection. Imagine the magnetar's crust under unimaginable strain from the twisted internal magnetic field suddenly cracking. This starquake could launch a powerful shockwave into the magnetosphere, the dense cloud of plasma trapped by the magnetic field. As this shockwave propagates, it could accelerate electrons to near light speeds, causing them to spiral along magnetic field lines and emit a coherent, lighthouse-like beam of radio waves in a process known as synchrotron maser emission. It's akin to the crack of a whip translating kinetic energy into a sound wave, but on a scale where the whip is the crust of a star and the sound is a blast of radio energy visible across the galaxy. However, the details are incredibly complex. Why do some magnetar eruptions produce bright X-ray flares while only some produce these brilliant radio bursts? The answer may lie in the environment around the magnetar. If the magnetosphere is filled with just the right density of plasma, the conditions might be perfect for amplifying a shock wave into an FRB. If the plasma is too dense or too thin, the process might fizzle or manifest as a different type of flare. Furthermore, the fact that most FRBs from distant galaxies do not seem to repeat, while our galactic magnetar has produced only one such detected FRB amid many X-ray outbursts, suggests that producing a fast radio burst might be a rare and specific set of circumstances even for a magnetar. It might require a very particular type of starquake, a specific alignment of the magnetic field, and a perfect plasma cocktail in the magnetosphere to focus the energy into the radio burst we can detect. The detection from within our galaxy turned magnetars from a compelling suspect into a confirmed source, but it also revealed that their inner workings are even more complex and fascinating than we had imagined. After exploring the fleeting fury of magnetars and the brief, brilliant enigmas of fast radio bursts, we must now turn our gaze to the greatest explosion of all, one that was not merely an event in the universe, but the very origin of the universe itself. Every cataclysm we have discussed, from supernova to colliding black holes, is a dramatic episode in a cosmic story that began with the ultimate energetic event, the Big Bang. This was not an explosion of matter expanding into a pre-existing void, like a bomb detonating in silent, empty space. Instead, it was the simultaneous creation and expansion of space and time from a state of infinite density and temperature, a singularity where the very laws of physics as we know them break down. To call it the biggest bang is almost an understatement. It was the moment that defined the concepts of energy, matter, and existence. In its first fleeting instance, the universe was an indescribably hot, dense soup of pure energy. There were no atoms, no protons, no neutrons, just fundamental forces and particles merging and separating in a searing maelstrom. Within the first second, the universe expanded and cooled at a rate that is almost impossible to comprehend, allowing the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces to separate from their unified state. Energy began to condense into the first particles of matter and antimatter, which mostly annihilated each other back into energy in a furious blaze. But a tiny, crucial asymmetry, perhaps just one extra particle of matter for every billion particle-antiparticle pairs, left behind the raw material for everything we see today. Every single atom in every star, every planet, and in our own bodies is a relic from that 1 in a billion survival, a testament to the sheer, unfathomable energy of that initial state. What makes the Big Bang fundamentally different from every other explosion we've studied is that it created the very stage upon which all subsequent explosions would play out. A supernova occurs within the framework of existing space and time. The Big Bang was the creation of that framework. The expansion we observe today in the redshifting of distant galaxies is not the aftermath of an explosion that happened long ago. It is the ongoing, direct result of that initial event. The cosmic microwave background radiation, a faint glow of heat that permeates all of space, is the cooled and stretched remnant of the universe's first light, released when it had cooled enough for atoms to form and space to become transparent, about 380,000 years after the beginning. This afterglow is the most ancient light we can observe, and it serves as the ultimate fossil evidence for the hot, dense origin of the cosmos. While the Big Bang stands alone as the singular event that set everything in motion, its profound legacy is that it made all the other cosmic explosions possible. It generated the primordial hydrogen and helium that would collapse into the first stars. Those stars, in their lives and deaths, forged the heavier elements through the very supernova and kilonova processes we've explored. The gravitational structures that grew from tiny fluctuations in the early universe eventually became the galaxies that host active galactic nuclei and the binary systems that produce gamma-ray bursts. In this grand perspective, the Big Bang is not just another entry on a list of energetic events. It is the foundational cataclysm from which all subsequent violence, creativity, and complexity in the universe arose. It is the original explosion whose echoes are still shaping cosmic history 14 billion years later, and whose energy continues to fuel the life cycles of stars, the formation of planets, and the very possibility of our existence. Just as the fading light of a supernova afterglow tells the story of a stellar explosion, the entire cosmos is filled with the ultimate afterglow from the most profound explosion of all, the cosmic microwave background radiation. This is not the echo of a single star's death, but the cooled remnant of the universe's very first light, a snapshot of a time when everything was fundamentally different. Imagine the universe about 380,000 years after the Big Bang. Before this moment, the cosmos was an opaque, searing fog of plasma, so dense and hot that light particles, photons, couldn't travel any meaningful distance before being scattered by free electrons. It was a brilliant but featureless glow. Then, as the universe expanded and cooled, it crossed a critical threshold. The temperature dropped enough for protons and electrons to combine and form neutral hydrogen atoms in an event called recombination. Suddenly, the fog lifted, the universe became transparent, and those photons, which had been trapped for millennia, were finally set free to travel across space. What we detect today as the cosmic microwave background is that very same light, but it has been on an incredible journey. After traveling for over 13 billion years, the expansion of the universe has dramatically stretched the wavelength of that primordial light. The once brilliant, visible light glow has been redshifted all the way down into the microwave part of the electromagnetic spectrum, corresponding to a temperature of just 2.7 degrees above absolute zero. This is why it appears to us as a faint, cold, and nearly uniform microwave signal that comes from every direction in the sky. If you could see microwaves, the entire night sky would appear to glow with a dull, uniform light. It is the oldest light we can possibly observe, a direct messenger from the universe's infancy, and its discovery in the 1960s was the conclusive evidence that cemented the Big Bang theory as the dominant model of cosmic origins. The true power of the CMB, however, lies not in its uniformity but in its tiny imperfections. While the background is incredibly smooth, sensitive satellites like NASA's Cosmic Background Explorer, or COBE, and later the Planck mission, have mapped it with exquisite precision, revealing minute temperature fluctuations, tiny variations of only 1 part in 100,000. These are the cosmic seeds from which all structure in the universe grew. Those slightly denser, slightly warmer patches in the early universe had a tiny bit more gravitational pull, attracting more matter over billions of years. They were the gravitational wells that would eventually collapse to form the first stars, the first galaxies, and the vast cosmic web of filaments and voids we see today. By studying the pattern of these fluctuations, cosmologists can determine the fundamental ingredients of the universe, the amount of ordinary matter, the mysterious dark matter, and the nature of dark energy with incredible accuracy. The CMB is therefore far more than a simple afterglow. It is the universe's blueprint, a fossilized imprint of its initial conditions that allows us to read the story of its entire evolution, from a hot, dense beginning to the complex cosmos we inhabit now. The story of cosmic explosions is not just about the past, It is also a key that unlocked one of the most profound and unsettling mysteries of our present-day universe. For much of the 20th century, astronomers operated under a straightforward assumption. After the initial fireball of the Big Bang, the expansion of the universe should be slowing down. The mutual gravitational pull of all the matter in the cosmos, the galaxies, the stars, the dark matter should act like a cosmic brake, gradually decelerating the flight of galaxies away from one another. The central question was whether there was enough matter to eventually halt the expansion and pull everything back together in a big crunch, or if the universe would simply coast forever, expanding at an ever-slowing rate. Then, in the late 1990s, two independent teams of astronomers set out to measure this deceleration by using a very specific kind of cosmic explosion as a standard candle, the type Ia supernova. You'll recall that these supernovae, born from the thermonuclear detonation of a white dwarf star, have a remarkably consistent peak brightness. This consistency makes them perfect for measuring vast cosmic distances. If you know how bright the explosion should be, and you measure how bright it appears from Earth, you can calculate precisely how far away it is. The teams, led by Saul Perlmutter and separately by Brian Schmidt and Adam Rees, were looking at extremely distant type Ia supernova whose light had been traveling for billions of years. By comparing these distances to the redshifts of the supernova's host galaxies, they could chart how the expansion rate of the universe had changed over cosmic time. They expected to see that the more distant supernova representing a younger universe were receding from us at a faster rate than the closer ones, showing the signature of a gradual slowdown. What they found instead sent shockwaves through the world of physics. The distant supernova were significantly fainter than their models predicted. This meant they were farther away than they should have been if the universe had been expanding at a steady or decelerating pace. The only logical conclusion was that the expansion of the universe was not slowing down at all. In fact, it was speeding up. Some mysterious force was acting against gravity, pushing galaxies apart with ever-increasing vigor. The discovery was so unexpected and bizarre that the teams spent years checking and rechecking their data for errors, from the possible dimming by interstellar dust to subtle evolutionary effects in the supernova themselves. But the result held firm. In 1998, they announced their findings, which would later earn them the Nobel Prize in Physics. The universe, against all expectations, was undergoing an accelerated expansion. This revelation demanded a physical explanation, and the leading candidate is what we now call dark energy. It is not a substance in the traditional sense, but rather a property of space itself. The simplest interpretation, based on Einstein's own equations, is that empty space is not nothing. It possesses a fundamental energy density, often referred to as a cosmological constant. This energy has a negative pressure, and according to the rules of general relativity, this negative pressure generates a repulsive gravitational effect. As the universe expands and more space comes into existence, more of this repulsive energy appears, causing the expansion to accelerate further. The implications are staggering. Current measurements indicate that dark energy makes up about 68% of the total energy content of the universe, with dark matter comprising about 27%, and all the normal matter that makes up stars, planets, and us, accounting for a mere 5%. The fate of the cosmos, it seems, is not ruled by the gravity of matter, but by the hidden energy of the vacuum. The ultimate fate of the universe now appears to be a cold and lonely one. If dark energy continues to dominate as it does today, the acceleration will continue indefinitely. In the far, far future, galaxies outside our local group will be pushed away from us so quickly that their light will no longer be able to reach us. The universe will become a much darker place, with the cosmic background radiation fading away and the evidence for the Big Bang becoming inaccessible. This Big Rip scenario, while not certain, paints a picture of a cosmos where the very fabric of space itself is the most powerful explosive force of all, silently and relentlessly tearing the universe apart. It is a humbling thought that our understanding of this grand cosmic destiny was illuminated by the brilliant, self-destructing death throes of white dwarf stars, turning the final moments of a star into a beacon that revealed the deepest secret of the cosmos. This remarkable consistency in their peak brightness is what elevates Type Ia supernova from being merely spectacular stellar deaths to being indispensable tools for cosmology. They act as what astronomers call standard candles. Think of it this way: if you were standing on a long, dark road at night and you saw two identical 100-watt light bulbs, one close by and one far away, the farther bulb would appear dimmer. By knowing the true wattage of the bulb and measuring how dim it looks, you could actually calculate your distance to it. Type Ia supernovas serve as the universe's ultimate 100-watt light bulbs. Because the physics of their detonation is always triggered at the same critical mass, the Chandrasekhar limit of about 1.4 solar masses, the amount of radioactive nickel they create and the resulting luminosity of the explosion are incredibly uniform. This gives astronomers a known, standard intrinsic brightness to work with. The practical application of this is nothing short of revolutionary for measuring the cosmos. When a Type Ia supernova is discovered in a distant galaxy, astronomers urgently measure its light curve, how its brightness changes over time. The peak of that curve is then compared to the known standard brightness. The difference between how bright it should be and how bright it appears to be directly translates into a precise distance measurement, a concept known as the distance modulus. This method is so powerful that it allows us to gauge distances to galaxies billions of light years away, far beyond the reach of other measurement techniques like parallax. It was this very tool that enabled one of the most startling discoveries of the 20th century. By meticulously observing distant Type Ia supernova, two independent teams of researchers made a Nobel Prize-winning discovery in the late 1990s. They expected to find that the expansion of the universe set in motion by the Big Bang was slowing down over time due to the gravitational pull of all the matter in the cosmos. Instead, their measurements revealed the exact opposite. The supernova were fainter than expected, meaning they were farther away than their redshifts indicated they should be. The only possible explanation was that the expansion of the universe is not slowing down, it is accelerating. This revelation pointed to the existence of a mysterious repulsive force, now dubbed dark energy, which makes up about 70% of the universe's total energy content and is shaping the ultimate fate of the cosmos. Without the reliability of Type Ia supernova as standard candles, this profound shift in our understanding might have remained hidden. They provide a crucial rung on what astronomers call the cosmic distance ladder, connecting nearby distances measured by parallax to the far reaches of the observable universe. Each supernova detection is like another data point on a grand graph of the cosmos, allowing scientists to chart the expansion history of the universe with ever-increasing precision. So, the next time you hear about a supernova discovery, remember that it's more than just a cosmic spectacle. It is a vital piece of data, a beacon in the darkness that helps us map the geometry, the history, and the mysterious energy contents of the universe itself. This profound connection between cosmic violence and our own existence is perhaps the most humbling and awe-inspiring fact of all. Every element that makes up our bodies, our planet, and the technology we use was forged in the heart of a star or the aftermath of a cataclysm. The story begins with the Big Bang, which acted as a vast primordial furnace. But this initial burst of creation was surprisingly limited, producing only the three lightest elements, vast amounts of hydrogen and helium, with just a trace sprinkling of lithium. For millions of years, the universe was a simple, boring place, a dark, expanding sea of these light gases with no planets, no chemistry, and certainly no life. The potential for complexity was locked away, waiting for the first generations of stars to ignite and begin their transformative work. Inside the nuclear furnaces of stars, the real alchemy began. Through the process of nuclear fusion, stars like our Sun spend their lives fusing hydrogen into helium, releasing the energy that makes them shine. But for stars more massive than our Sun, the story doesn't end there. As they age, their cores become layered like a cosmic onion. In successive shells, they fuse helium into carbon, carbon into oxygen, and so on, building progressively heavier elements like neon, magnesium, and silicon, all the way up to iron. This stellar nucleosynthesis is a slow, steady cookery that creates the fundamental building blocks of rocky planets and, ultimately, life itself. The carbon that forms the backbone of every organic molecule in your body, the oxygen that fills your lungs with every breath, and the calcium that strengthens your bones, all were crafted in the intense heat and pressure of a living star. But there is a critical limit to this process. Fusing elements up to iron releases energy, which provides the outward pressure that holds the star up against the crush of gravity. However, fusing iron consumes energy. It is the star's ultimate poison pill. Once a massive star builds an iron core, its central engine sputters and dies. The result is a core collapse supernova, the very explosion that becomes the delivery mechanism for all these newly forged elements. The cataclysmic shockwave blasts the star's enriched outer layers into the interstellar medium, seeding vast clouds of gas and dust with this stellar ash. This scattered material contains not just the elements made during the star's life, but also new, even heavier elements synthesized in the incredible heat of the explosion itself, like sulfur, calcium, and titanium. For the very heaviest elements on the periodic table, however, even a supernova isn't quite enough. The creation of gold, platinum, uranium, and other atoms heavier than iron requires an even more extreme environment, one flooded with free neutrons. This is where the kilonova, the collision of two neutron stars, plays its essential role. In the frantic, neutron-rich debris of such a merger, atomic nuclei can capture neutrons at an astonishing rate through the rapid neutron capture process, or R process. In a matter of seconds, this process can build up lightweight elements into the heavy treasures we value so highly. The gold in a wedding ring, the platinum in a catalytic converter, and the iodine essential for our thyroid function were all born in the violent chaos of a neutron star collision billions of years ago. We are, therefore, the legacy of these cosmic explosions in the most literal sense possible. The iron that carries oxygen in your blood was forged in the core of a star that died in a supernova before our Sun was even born. The phosphorus that is a key component of your DNA was likely synthesized in that same explosion. The iodine that regulates your metabolism was cast into space by a kilonova. When we look up at the night sky, we are not just distant observers of these events, we are active participants in their aftermath. Our planet, our bodies, and every material thing we know are composed of atoms that were created in the lives and deaths of stars, scattered across the galaxy by the universe's most energetic explosions, and then gathered together by gravity to form our world. We are not just living in the universe is living in us. To truly appreciate the legacy of a supernova, we need to move beyond abstract concepts and witness the artistry of a specific, breathtaking example. Let's turn our gaze to a corner of the constellation Cygnus, the Swan, where a celestial tapestry known as the Veil Nebula drifts through space. This is not a gentle cloud of gas, it is the shattered, glowing wreckage of a star that met its end between 10 and 20,000 years ago. What we see today is the expanding shockwave from that ancient cataclysm, a bubble of debris so vast that even though it lies about 2,400 light-years away, it spans an area of the sky equivalent to 6 full moons. Through a small telescope, it appears as a faint, wispy filament, but when the Hubble Space Telescope turns its powerful eye toward it, the view is transformed into a masterpiece of cosmic violence and beauty. The intricate structure of the Veil Nebula is a direct result of the explosive forces that created it. The nebula isn't a smooth, homogeneous cloud. Instead, it's a complex network of delicate, intertwined filaments. Each thread and ripple you see is a part of the single, spherical shockwave that has been expanding for millennia. As this shell of energy races outward at hundreds of thousands of miles per hour, it doesn't move through a perfectly uniform void. It encounters pockets of interstellar gas of slightly different densities. The shockwave plows through less dense regions more easily, while it slows and piles up against denser clumps. This interaction over thousands of years has sculpted the smooth sphere of the initial blast into the intricate, lace-like structure we observe today. It's a cosmic fossil record, preserving the turbulence and texture of the interstellar medium itself. Now, let's talk about the stunning palette of colors that makes the Veil Nebula so photogenic. Those brilliant hues are far more than just pretty pictures. They are a direct chemical fingerprint, a neon sign announcing the elemental composition of the exploded star. The specific colors correspond to different gases being heated to incandescence by the immense energy of the shockwave. The most prominent color is a vivid, ethereal red, which comes from hydrogen gas. When hydrogen atoms in the shockwave are excited by the passing energy, their electrons jump to a higher energy state. As they fall back down, they emit a characteristic red light at a specific wavelength. This red glow dominates large sections of the nebula, tracing the outline of the expanding bubble. But look closer and you'll see dazzling filaments of electric blue and green. These colors are the signature of oxygen atoms. However, the oxygen isn't glowing in the same way. The shockwave is so powerful that it actually strips electrons away from the oxygen atoms, ionizing them. It is the recombination of these ionized oxygen atoms with their lost electrons that produces the brilliant blue-green light. In some regions, you can even see subtle hints of other colors. Sulfur glows with a more subdued red, while nitrogen contributes other shades. By mapping these colors, astronomers can perform a kind of cosmic chemistry, determining not only what the star was made of, but also how different elements were distributed by the explosion. The Veil Nebula is a spectacular demonstration that the universe has its own periodic table of light, and supernova remnants are its most brilliant display. While the delicate filaments of the Veil Nebula show us the slower, cooling phase of a supernova's aftermath, there's another nearby remnant where the action is far more immediate and violent. Shifting our gaze to the southern constellation of Vela, the Sail, we find the Vela supernova remnant, the expanding debris cloud from a star that exploded a mere 11 or 12,000 years ago. So recently in cosmic terms that our prehistoric ancestors may have witnessed its brilliant light in the night sky. This vast structure, spanning over 100 light years, is a spectacular sight in its own right, but the true heart of the drama lies at its very center. There, spinning with incredible speed, is the Vela pulsar, a city-sized neutron star that is not just a silent monument to the explosion, but an incredibly active engine, continuously pouring energy back into its surroundings and creating a phenomenon known as a pulsar wind nebula. The Vela pulsar itself is a cosmic powerhouse. It rotates about 11 times every single second, which is remarkably fast for an object containing more mass than our Sun. With each rotation, its powerful magnetic fields funnel radiation into twin beams, and one of those beams sweeps across Earth, making it appear to pulse in radio waves, visible light, and even gamma rays. But the pulsar's influence extends far beyond its lighthouse-like beams. It is also blowing a relentless, supersonic gale of charged particles, electrons, and positrons out into space. This outflow is known as the pulsar wind, and it moves at nearly the speed of light. When this ultra-relativistic wind slams into the slower-moving gas of the surrounding supernova remnant, it doesn't just push it aside. It creates a spectacular, structured shockwave that lights up the nebula. The result is a dynamic and intricate structure that astronomers can study in incredible detail because of its relative proximity, only about 800 light-years away. The pulsar wind nebula within the Vela remnant glows brightly across the electromagnetic spectrum. In X-ray images, we see delicate, arc-like structures where the pulsar wind is colliding with the remnant's material, energizing it to millions of degrees. Invisible light, filamentary loops and tendrils of gas reveal the complex interplay between the ancient supernova shockwave and the fresh energy being injected by the pulsar. This makes the Vela system a perfect natural laboratory. We are watching in real time how a pulsar gradually loses its rotational energy and how that energy gets transferred to re-energize the expanding shell of its own birth cloud. It's a feedback loop on a cosmic scale, showing that the death of a star isn't a single event, but a process that can continue to shape its local environment for tens of thousands of years. Perhaps the most astonishing property of the Vela pulsar is that it is one of the brightest persistent sources of gamma rays in our entire sky. This is not the brief flash of a gamma ray burst, but a steady, brilliant beacon of the highest energy light. The mechanism for this is thought to occur in the pulsar's outer magnetosphere, where intense electric fields generated by the spinning magnetic field can accelerate particles to such fantastic energies that they emit gamma-ray photons. The fact that we can detect such a powerful and steady stream of gamma rays from a single, tiny object underscores the almost unbelievable energy densities involved in the environment around a neutron star. By studying this persistent gamma-ray glow, along with the nebula's structure, scientists gain crucial insights into the fundamental physics of particle acceleration and magnetic field dynamics under conditions that are impossible to recreate in any laboratory on Earth. The Vela pulsar and its nebula serve as a constant reminder that the aftermath of a supernova can be just as violent and informative as the explosion itself. Now, shifting our focus from the ancient echoes of past explosions to a potential future cataclysm, we come to a star system that feels like a cosmic time bomb ticking in our own galactic neighborhood. Nestled within the Carina Nebula, a vast stellar nursery about 7,500 light-years away, lies Eta Carinae, a hypergiant binary system that is quite possibly the most unstable and dangerous star known to humanity. This isn't a quiet, distant point of light. It is a seething, volatile behemoth that has already given us a dramatic preview of its destructive potential. Eta Carinae is a system dominated by not one, but two colossal stars locked in a frantic 5.5-year orbital dance. The primary star is a true monster, estimated to be anywhere from 100 to 200 times the mass of our Sun, making it one of the most massive stars we can directly study. Its companion is no less impressive, weighing in at around 30 solar masses. Together, they form a gravitational partnership fraught with instability, and their interactions have already written a spectacular chapter in astronomical history. That history includes an event so violent it was mistaken for a supernova in the 19th century. In the 1840s, Eta Carinae underwent what astronomers now call a great eruption. Over a period of about 20 years, it became the second brightest star in the night sky, despite its immense distance, at one point even rivaling the brilliance of Sirius. This was not a true supernova the star survived, but rather a colossal stellar tantrum, a supernova imposter event. The eruption blasted off an enormous amount of material, creating the beautiful bipolar lobes of gas and dust we see today, known as the Homunculus Nebula. This nebula, which expands outward from the star system, is essentially the shrapnel from that ancient explosion, and it contains enough mass to make several copies of our Sun. The cause of this eruption is still debated, but it likely involved a massive buildup of radiation pressure within the star, or perhaps a violent interaction with its companion that caused its outer layers to be violently ejected without completely destroying the core. Today, Eta Carinae remains in a highly unstable state. It is racked by violent pulsations and experiences regular, smaller eruptions as it teeters on the edge of stability. The star is so massive that the outward pressure of radiation from its core battles fiercely against the immense inward pull of its own gravity. This balance is precarious. The star is losing mass at a phenomenal rate through a powerful stellar wind, and its lifetime is measured in mere thousands, perhaps even hundreds of years, rather than the billions of years allotted to a star like our Sun. Every observation we make is a snapshot of a star in its final, frantic act. This leads to the thrilling and slightly unnerving speculation: when will Eta Carinii finally go supernova? The truth is, it could happen at any moment. In cosmic terms, its death is imminent. Given the 7,500-year journey that its light must take to reach us, it is entirely possible that Eta Carinii has already met its fiery end, and the photons carrying the news of its destruction are currently speeding across the void toward Earth. We are essentially watching a pre-recorded cosmic drama, never knowing if the final scene has already been filmed. When that light does arrive, the spectacle from Earth would be unlike anything witnessed in recorded human history. A supernova from Eta Carinii would not be a subtle event. Astronomers predict it could become brilliantly visible in the daytime sky, potentially as bright as the full moon. At night, it would cast sharp shadows and be visible for months or even years to the naked eye as a dazzling new star in the southern constellation of Carina. But the spectacle would be more than just visual. The explosion would likely be a hypernova associated with a long-duration gamma-ray burst. Thankfully, the system's rotational axis is thought to be tilted away from us, meaning the deadly jets of such a burst would probably not be pointed directly at Earth. Even so, the event would provide an unprecedented opportunity for science, allowing us to study every facet of a stellar death in incredible detail, from the initial shock breakout to the formation of its remnant. Eta Carinii is a constant reminder that the cosmos is a dynamic and violent place, and that one of the greatest shows in the universe might be waiting just offstage, its starting cue already given. But perhaps the most dramatic and consequential outcome of this celestial dance is the one we've already explored, the Type Ia supernova. This entire cataclysmic sequence relies utterly on the binary partnership. It begins with a white dwarf, the Earth-sized remnant of a Sun-like star, gravitationally bound to a companion, often a red giant. The white dwarf acts as a cosmic vampire, siphoning a stream of hydrogen-rich gas from its partner. This material accumulates on the white dwarf's surface, building pressure and heat until it ignites in the periodic flare-ups we see as nova. But if the rate of accretion is just right, if the white dwarf can hold onto a tiny fraction of this stolen mass after each nova eruption, a slow and steady countdown begins. Over thousands or millions of years, the white dwarf's mass creeps ever closer to the Chandrasekhar limit of about 1.4 solar masses. Upon reaching this threshold, the entire star is no longer stable. A runaway thermonuclear fusion reaction rips through the white dwarf from its core to its surface, completely annihilating it in an explosion so standardized and brilliant that it can be used to measure the expansion of the universe itself. Without the steady fuel supply provided by a binary companion, this specific universe-calibrating type of explosion simply would not occur. The influence of binary systems extends deeply into the lives and deaths of the most massive stars as well, directly shaping the conditions that can lead to gamma-ray bursts. For a star to produce a long-duration GRB, it isn't enough for it to be massive. It also needs to be rapidly rotating right up to the moment of its core collapse. This rapid spin is crucial for forming the accretion disk and powering the relativistic jets that characterize a GRB. But a massive, single star tends to lose its rotational momentum through its own powerful stellar winds. A binary companion, however, can act as a cosmic spinning top. Through gravitational interactions, particularly if the stars are close enough for tidal forces to lock their spins, a binary partner can keep a massive star rotating quickly throughout its short life. Furthermore, in some scenarios, the binary interaction itself can strip away the star's outer hydrogen envelope long before its death. This leaves behind a bare, rapidly spinning Wolf-Rayet star, the perfect progenitor for the quasar model of a gamma-ray burst. In these cases, the presence of a companion star essentially pre-processes the massive star, tailoring its properties to ensure its death is not just a supernova, but a hyper-energetic, jet-driven event visible across the cosmos. Even the spectacular finale of a kilonova, the collision of two neutron stars, is a story that begins millennia earlier in a binary system. Two massive stars are born together, evolve together, and often explode as supernova one after the other. If the supernova explosions are not perfectly symmetric and don't kick the resulting neutron stars completely apart, the binary bond can survive. The two ultra-dense stellar corpses are then left to orbit one another in an increasingly tight spiral, their orbital energy slowly being radiated away as gravitational waves over hundreds of millions of years. Their fate is sealed from the moment of their birth as a binary pair. Their eventual merger, which forges heavy elements like gold and platinum and produces a short gamma-ray burst, is the direct and inevitable consequence of their shared stellar history. From the gentle flicker of a nova to the planet-sterilizing beam of a gamma-ray burst, the intricate gravitational interplay between two stars is a fundamental catalyst, turning solitary stellar evolution into the most energetic and transformative explosions in the universe. Given how brief and violent these cosmic explosions are, how can we possibly hope to understand the intricate physics happening deep inside a collapsing star or at the heart of a merging black hole? The answer lies not just in our telescopes, but in some of the most powerful supercomputers on the planet. These machines allow us to create virtual universes, running incredibly detailed simulations that model the unseeable. It's a form of scientific time travel where we can rewind a cataclysm, slow it down to a crawl, and examine every single step of the process from every possible angle. These simulations are not just fancy animations, they are complex mathematical experiments that solve the fundamental equations of physics, general relativity, magnetohydrodynamics, and nuclear physics across billions of points in space and time. Consider the challenge of a core collapse supernova. For decades, a major puzzle known as the supernova problem lingered. Simple models showed that the initial shockwave from the collapsing core should stall, failing to actually blow the star apart. Observations, however, clearly showed that stars do explode. The missing ingredient, it turns out, was buried in physics too complex for simple calculations. Modern supercomputer simulations can now model the star's interior in 3 dimensions, capturing the chaotic, turbulent convection that occurs as neutrinos flood out from the newborn neutron star. These simulations reveal that this turbulence helps re-energize the shockwave, like a series of secondary explosions pushing from behind, ultimately reviving it and driving the successful supernova. Without these multi-dimensional models, we might still be wondering how stars manage to tear themselves apart. The formation of a gamma-ray burst relativistic jet is another process entirely reliant on simulation. The interplay between a black hole's gravity, the insane rotation of the surrounding accretion disk, and the dynamics of magnetic fields is a problem so complex it can only be solved numerically. Researchers start with the initial conditions, a massive, rotating star or 2 merging neutron stars, and let the laws of physics play out. The simulations show how magnetic fields can be wound up like cosmic springs by the disk's rotation, eventually launching and collimating the narrow jets that punch their way out of the stellar envelope. By tweaking the initial parameters like the star's rotation rate or magnetic field strength, scientists can test which conditions produce a successful jet and which result in a fizzled explosion. This helps explain why gamma-ray bursts are so rare. they require a very specific and precise set of circumstances to occur. These digital laboratories are also essential for interpreting the signals we receive from gravitational wave observatories like LIGO and Virgo. When two black holes or neutron stars spiral together, the gravitational wave signal we detect is a unique fingerprint of their masses, spins, and internal structure. To decode that fingerprint, researchers run vast libraries of simulations covering millions of possible merger scenarios. When a real signal is detected, they can compare it against this pre-computed library to find the best match, instantly telling them what kind of objects just collided and how the event unfolded. This is how we knew, for instance, that the event in 2017 was a neutron-star merger and not a black hole collision. The simulation didn't just confirm the event, it predicted the kind of electromagnetic afterglow we should look for, guiding telescopes to one of the most important astronomical discoveries of the century. Ultimately, these simulations act as a crucial bridge between theory and observation. A new observation might reveal a strange feature in a supernova's light curve or an unusual pattern in a gamma-ray burst. Theorists can then take that data and build a new simulation to test a hypothesis about what physical process could be responsible. It's a continuous cycle of prediction and refinement, where our digital models become increasingly sophisticated and accurate representations of reality. They allow us to probe environments where the density is 1 billion times that of a white dwarf and temperatures exceed 100 billion degrees, conditions so extreme they will never be replicated in any laboratory on Earth. In this way, supercomputer simulations have become our most powerful telescope, not for looking out into space, but for looking deep into the heart of cosmic violence itself. But while our telescopes capture the brilliant light of a supernova, the true story of the explosion begins with a silent, invisible exodus of particles so elusive they are called ghost particles. When a massive star's core collapses, the incredible gravitational energy released equivalent to the binding energy of an entire star has to go somewhere. Astonishingly, about 99% of that cataclysmic energy is not converted into the blinding flash of light we see. Instead, it is carried away by a vast flood of neutrinos, near massless particles that are born in the heart of the stellar collapse and pour out into the universe almost completely unimpeded. To understand why neutrinos are so central to this process, we need to look at the conditions inside the collapsing core. In the final second of a star's life, the core, which is about the size of Earth, is crushed into a city-sized neutron star. The pressure and density become so extreme that protons and electrons are forced together, merging to form neutrons and releasing a neutrino with each merger. Furthermore, the newborn neutron star is unimaginably hot, with temperatures exceeding 100 billion degrees. This heat energy is also converted into pairs of neutrinos and their antimatter counterparts, antineutrinos. In that single, violent second, a supernova can release more neutrinos than there are stars in the observable universe. This neutrino burst is the primary signal of the core's transformation, a direct telegraph from the very engine of the explosion. The ghostly nature of neutrinos is what makes them both a challenge and a unique opportunity for science. These particles have no electric charge and almost no mass, and they interact with matter only via the weak nuclear force. This means they can pass through almost anything as if it weren't there. A neutrino could travel through a light year of solid lead with only a 50% chance of being stopped. This is why, when that immense pulse of neutrinos leaves the supernova, it races ahead of the shockwave and the light, reaching us hours before the visible explosion brightens the star. They give us a direct, unadulterated look at the core collapse itself, unaffected by the complex physics of the star's outer layers that eventually produce the light show. This theoretical prediction was spectacularly confirmed in February 1987, when a star in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, went supernova. Designated Supernova 1987A, It was the closest observed supernova in centuries. Crucially, about 3 hours before the visible light from the explosion reached Earth, 3 neutrino observatories, Kamiok and in Japan, IMB in the United States, and Baksan in Russia registered a distinct burst of 24 neutrinos within a 13-second window. Considering the vast distance and the fact that trillions of neutrinos passed through each square centimeter of the detectors, catching 24 was a monumental success. That handful of particles was the smoking gun, the direct evidence that the core collapse model was correct. Those few detections confirmed that a neutron star had indeed formed in the heart of the explosion, and that neutrinos were the dominant carrier of the supernova's energy. The detection from supernova 1987 did more than just confirm a theory. It founded an entirely new field of astronomy, neutrino astronomy. For the first time, we had observed a cosmic event not with light but with another fundamental messenger. The properties of those detected neutrinos, their energies, and the duration of the burst provided crucial information about the temperature and size of the newly formed neutron star. Today, a new generation of vastly more sensitive detectors like Super Kamiok and in Japan and the upcoming deep underground neutrino experiment in the United States lies in wait. Their goal is to catch the neutrino signal from the next nearby supernova in our galaxy with unprecedented detail, allowing us to essentially watch a core collapse in real time. These ghostly messengers, born from the most violent birth in the universe, offer us a portal directly into the heart of the explosion, revealing secrets that light alone can never tell. Looking ahead, the next decade promises to transform our hunt for cosmic explosions from a patient observation into a real-time, all-sky surveillance operation. At the forefront of this revolution is the Vera C. Rubin Observatory, currently under construction in Chile. Its mission is almost unimaginable in its scope: to conduct a 10-year survey of the entire available sky, capturing a panoramic image every few nights with a camera containing over 3 billion pixels. This isn't just an upgrade, it's a paradigm shift. Instead of waiting for a lucky detection or focusing on a small patch of the universe, Rubin will be watching everything all the time. It's designed to discover millions of transient objects, things that change in brightness. This will include everything from nearby supernova in their very earliest hours to incredibly faint, distant explosions at the edge of the observable universe, effectively creating a high-definition movie of the dynamic cosmos and revealing events we can't even predict today. This optical avalanche of data will be complemented by a new era of gravitational wave astronomy. The current LIGO and Virgo detectors are marvels of engineering, but their successors, like the planned Einstein telescope in Europe and Cosmic Explorer in the United States, will be far more sensitive. These next-generation observatories will be built underground to reduce seismic noise and will feature arm lengths of 10 kilometers or even 40 kilometers compared to LIGO 4. This increased sensitivity will allow them to hear the cosmic symphony from a much greater volume of space, detecting black hole mergers from the very first billion years of the universe. More importantly, they will pick up these signals for much longer before the final merger, giving astronomers hours or even days of warning to point every other telescope at the predicted location. This will turn multi-messenger astronomy from a rare, frantic event into a routine scientific practice, allowing us to study the entire lead up to collisions in exquisite detail. The view from space is also set for a monumental upgrade. New missions are being developed to probe the highest energy phenomena across the electromagnetic spectrum. The European Space Agency's Athena X-ray Observatory will be a powerful tool for studying the hot, violent aftermath of explosions, such as the gas heated to millions of degrees in supernova remnants and the accretion flows around supermassive black holes. In the gamma-ray regime, new concepts aim to achieve better resolution and sensitivity, allowing us to pinpoint the sources of fleeting gamma-ray bursts and study the high-energy emission from magnetar flares and blazars with unprecedented clarity. These space-based eyes will be crucial for observing the energetic radiation that our atmosphere blocks, providing a complete picture of the explosive universe that is invisible from the ground. What makes this future so exhilarating is the power of synergy. It's not just about one new telescope, it's about all of them working in concert. Imagine an alert from the Rubin Observatory flagging a strange, new type of flash in a distant galaxy. Within minutes, an automated network of smaller, rapid-response telescopes could swing into action to capture its spectrum. At the same time, a gravitational wave detector might sense ripples from the same region of sky, confirming the event involved massive objects in motion. Space telescopes would then be commanded to observe the event in X-rays and gamma rays, while neutrino detectors scan their data for a coincident burst of ghost particles. This multi-messenger, all-wavelength approach will allow us to classify cosmic explosions with a precision we can only dream of today, revealing the underlying physics that drives them. We are on the cusp of moving from simply cataloging these events to truly understanding them, uncovering fainter, more distant, and entirely new classes of explosive phenomena that will undoubtedly challenge our current theories and open new chapters in our understanding of the universe's most energetic moments. But to truly understand where all these elements came from, we have to rewind the cosmic clock almost all the way back to the beginning, to a time before any stars had died, before any planets had formed, to the very first generation of suns. Astronomers call these mythical giants population 3 stars, and their existence is one of the most compelling hypotheses in modern cosmology. Picture a universe that is dark, simple, and pristine. The Big Bang has occurred, but all it has produced is a vast, expanding fog of hydrogen, helium, and a tiny trace of lithium. There are no rocks, no metals, no dust. There is nothing for light to reflect off of, and no complex chemistry can occur. Into this silent emptiness, gravity begins its patient work, slowly pulling together the first clumps of primordial gas. Because this gas was pure and lacked any of the heavier elements that help modern gas clouds cool and fragment efficiently, the first stars could grow to truly monstrous sizes. Theoretical models suggest that population 3 stars were not just large, they were behemoths, likely ranging from 100 to over 1,000 times the mass of our Sun. Imagine a star so colossal that it would make Eta Carinae look average. These stars would have lived incredibly fast and furious lives, burning through their nuclear fuel in only a few million years due to their immense gravity and heat. Their brilliance would have been staggering, shining with a ferocious blue-white light that was millions of times more luminous than our Sun. But their deaths would have been even more spectacular, and the nature of those final explosions would have set the course for all cosmic history that followed. The fate of these first stars depended critically on their mass. For the very largest among them, perhaps those between 140 and 260 solar masses, their deaths were likely unlike anything seen in the modern universe, a pair instability supernova. As we discussed earlier, this is a runaway thermonuclear explosion that leaves no remnant, completely obliterating the star. But for the absolute titans, those pushing 300 solar masses or more, the collapse may have been so extreme that it bypassed the pair instability mechanism altogether and formed a black hole directly. In some scenarios, the infall of material could have been so rapid and the rotation so fast that it powered a gamma-ray burst of almost unimaginable power, a hypernova, that would make today's long-duration burst seem tame by comparison. These first explosions were the universe's primary forges, responsible for creating and scattering the very first heavy elements, the first carbon, oxygen, silicon, and iron into the primordial darkness. This initial seeding was a cosmic act of fertilization. That first sprinkle of heavy elements blasted across space by the deaths of the population 3 stars fundamentally altered the universe forever. Subsequent generations of stars, known as population 2, and then our own Sun's generation, population 1, formed from gas clouds that were progressively more enriched with these metals. This enrichment allowed gas clouds to cool more efficiently and fragment into smaller clumps, which is why later generations of stars tend to be smaller and more numerous. The transition from the massive, solitary giants of population 3 to the more familiar stars of today was a direct result of that first wave of cosmic explosions. They quite literally set the stage for the possibility of rocky planets and ultimately life. Finding direct evidence of these first stars and their supernova is one of the holy grails of observational astronomy. The challenge is immense as these events occurred over 13 billion years ago. Their light is incredibly faint and has been stretched by the expansion of the universe into the infrared part of the spectrum. This is precisely the mission of the James Webb Space Telescope. With its powerful infrared eyes, JWST is peering back in time, searching for the chemical fingerprints of these first explosions in the light of the most distant galaxies. It is looking for galaxies that are unusually bright in certain infrared wavelengths, which could indicate the presence of large numbers of massive, pristine stars. Even more excitingly, it is on the hunt for a specific type of supernova signature, one that is extremely luminous and rich in certain elements but devoid of others, particularly iron, which would point to a pair instability event from a star that had never been polluted by previous generations. Every time JWST looks at a galaxy at the very edge of the observable universe, it is conducting a cosmic archaeological dig. The light it captures is a fossil record, encoding the composition of that galaxy and revealing the history of its star formation. Finding the signature of a population 3 supernova would be like discovering the first tool used by humanity, a relic that marks the moment the universe began its long journey from simplicity to the intricate complexity we see today. It would confirm our theories about the earliest moments of stellar life and reveal the specific cataclysms that forged the raw materials for everything that followed, connecting the violent birth of the first stars directly to our own existence. But for all their destructive power, these cosmic explosions are far more than just spectacular light shows. They have become some of the most valuable tools in the astronomer's toolkit, turning catastrophic events into precise instruments for measuring the universe itself. Think of it as using the universe's own natural fireworks as a sort of cosmic ruler, a time machine, and a chemistry set, all rolled into one. This transformation from object of study to essential tool is what truly unlocks the deepest secrets of the cosmos. The most classic example of this is the role of the Type Ia supernova as a standard candle. You'll recall that these explosions, triggered when a white dwarf reaches a critical mass, have a remarkably consistent peak brightness. This consistency is their power. In any field of science, if you have a light source of known intrinsic brightness, you can calculate its distance by measuring how dim it appears from your vantage point. It's the same principle as knowing that a 100-watt light bulb looks bright up close and faint from far away. Type Ia supernova are the universe's ultimate 100-watt bulbs. By discovering them in distant galaxies and measuring their apparent brightness, astronomers can calculate precise distances across billions of light years. It was this very method that led to the shocking discovery of dark energy and the accelerating expansion of the universe, proving that these stellar deaths are not just in points, but critical data points for mapping the largest scale behavior of the cosmos. Moving from the grand scale of cosmic expansion to the ancient history of star formation, we find gamma-ray bursts acting as unparalleled probes of the early universe. Because GRBs are so phenomenally energetic, they can be detected from the very edge of the observable universe, from a time when the cosmos was only a fraction of its current age. When the light from a distant GRB travels across the universe to reach us, it doesn't journey through empty space. It passes through vast clouds of gas and the halos of countless galaxies that lie between us and the burst. Each cloud imprints its own unique chemical fingerprint on the GRB's light, absorbing specific wavelengths. Astronomers can analyze this altered light, a technique called absorption spectroscopy, to take a detailed census of the material that existed along that line of sight billions of years ago. A single gamma ray burst backlighting the cosmos gives us a core sample of the universe's composition and structure across cosmic time, revealing how galaxies evolved and enriched the space between them with heavy elements. And then there are the kilonovae, which serve as our most direct window into the origin of the heaviest elements. For decades, the cosmic source of elements like gold, platinum, and uranium was a major mystery. The historic detection of a kilonova in 2017, associated with both gravitational waves and a short gamma-ray burst, provided the definitive answer. By analyzing the light from that kilonova, astronomers saw the direct spectral signatures of these heavy elements being forged in real time through the rapid neutron capture process. In this case, the explosion was not just a tool for measurement, but a live demonstration of cosmic alchemy. Each kilonova we observe is a natural laboratory for nuclear physics under the most extreme conditions imaginable, conditions we could never hope to replicate on Earth. They reveal the specific nuclear reactions that built the periodic table, and by extension, the very materials that make up our technological world and even parts of our own biology. Ultimately, these events are more than just subjects we study. They are active partners in our quest for knowledge. A supernova is a beacon that helps us measure the geometry of the universe. A gamma-ray burst is a flashlight that illuminates the cosmic web across billions of years. A kilonova is a factory whose production lines we can observe from a safe distance. By learning to read the signals from these violent events, we turn the chaos of stellar death into an ordered language that tells the story of the cosmos, from its earliest moments to its ultimate fate. They are the universe's way of providing the tools we need to understand it, transforming cataclysm into clarity. So let's take a final, humbling moment to truly absorb the sheer scale of the energies we've been discussing. We can talk about numbers quintillions, octillions, the power of 10, but these figures are so vast they become abstract, losing all connection to our terrestrial experience. To grasp it, we need to bring it down to a human level. Consider this: the total amount of energy consumed by all of human civilization throughout its entire history, from the first fires of prehistoric hominids to the global power grids of today, is a staggeringly large number. And yet, that entire cumulative output is utterly dwarfed by the energy a single, typical supernova releases in the very first second of its explosion. Everything we have ever built, powered, or accomplished as a species is but a whisper compared to the cosmic scream of one dying star. This isn't just about raw power, it's also about concentration. Think of the most powerful laser we can build on Earth, perhaps the National Ignition Facility, which focuses immense energy onto a tiny pellet for a fraction of a second. Now imagine that principle scaled up to a cosmic level with a gamma-ray burst. A GRB takes the energy of a supernova, itself an almost incomprehensible quantity, and instead of letting it expand in a sphere, it focuses it into two pencil-thin jets. The concentration of energy in those jets is so extreme that it defies any earthly analogy. If you could somehow create a similar level of focused energy on Earth, it would be like condensing the entire output of the Sun for its multi-billion-year lifespan into a beam no wider than a planet, firing for a few seconds. This is the realm of physics where matter is no longer solid, where magnetic fields are strong enough to warp the vacuum of space itself, and where particles are accelerated to energies that make our largest particle colliders seem like modest toys. Studying these events is not merely an academic exercise, it is a fundamental test of our deepest laws of physics. The conditions within a collapsing stellar core, at the moment a black hole is born, or inside the relativistic jet of a gamma-ray burst are so extreme that they push our understanding of reality to its absolute breaking point. Here, general relativity and quantum mechanics, the two pillars of modern physics, are forced to interact in ways we cannot yet fully describe. The densities approach and even exceed that of an atomic nucleus, creating states of matter that have no name. The temperatures are so high that particles behave in ways we can only theorize about. By observing the light, the gravitational waves, and the neutrinos from these cataclysms, we are essentially running nature's ultimate experiments, probing regimes of energy and density that we will never, ever be able to recreate in a laboratory on Earth. This pursuit forces us to confront the very nature of matter, energy, and gravity under duress. What happens to matter when it is squeezed to infinite density at the heart of a black hole? How do magnetic fields behave when they become the dominant force in the universe? What is the true equation of state for the hyperdense matter inside a neutron star? These are not just questions for astronomers, they are questions for fundamental physicists. Each new observation of a cosmic explosion is a data point that helps us refine our theories, challenging our assumptions and occasionally leading to revolutionary breakthroughs, just as the study of supernova led us to the dark energy that dominates the cosmos. In the end, these titanic explosions are more than just distant spectacles. They are our most powerful portals into understanding the universe at its most violent and fundamental level, reminding us that from the greatest destruction comes the deepest insight. And so we arrive at the ultimate, humbling truth that connects every one of these 50 facts directly to you, the observer. Every time an astronomer points a telescope at a distant supernova or a satellite catches the fleeting flash of a gamma-ray burst, we are not just collecting data, we are engaging in a profound form of time travel. The light from these cataclysms is a messenger from the deep past, and we are the intended recipients, living in the moment when its billion-year journey finally concludes. That pinprick of light in the eyepiece or on the monitor is not a report of something happening now. It is the ghost of an event that concluded when Earth was a barren rock, or before our planet had even coalesced from the cosmic dust. This delay between an event and our observation of it is not a shortcoming of our technology. It is a fundamental feature of the universe dictated by the finite, if incredibly fast, speed of light. Over interstellar and intergalactic distances, this speed limit becomes a time machine. The light from the nearby Andromeda galaxy, for instance, takes 2.5 million years to reach us. We see it not as it is today, but as it was when early hominids were first walking the plains of Africa. When we observe a supernova in a galaxy 100 million light-years away, we are witnessing a stellar death that occurred during the age of the dinosaurs. And the most distant gamma-ray bursts allow us to peer back to an era when the universe was less than a tenth of its current age, a time when the first stars were still lighting the cosmic darkness. Our telescopes are not just windows into space, they are portals into the epic history of the cosmos. This makes every one of us a witness to cosmic history on a scale that is almost impossible to comprehend. The photons that strike the mirror of the Hubble Space Telescope or the sensor of the James Webb Space Telescope have been traveling through the void, untouched and unobserved for eons. They have passed through the empty stretches between galaxies, their paths barely bent by the gravity of unseen dark matter. They have been on their solitary journey since before the solar system was born, since before the Milky Way took its current spiral shape. In the moment we detect them, we are completing a circuit that began at the scene of a cosmic catastrophe unimaginably long ago. We are the audience arriving for a show that started billions of years before we took our seats. This perspective transforms our place in the universe from passive inhabitants to active participants in a grand historical narrative. By collecting this ancient light and decoding its secrets, we are assembling the story of how the cosmos evolved from a simple, hot plasma into the complex, structured, and life-giving universe we see today. We are piecing together the life cycles of stars we will never visit, understanding the deaths of giants that died to create the very atoms that constitute our bodies. The iron in your blood, the calcium in your bones, and the oxygen you breathe are all souvenirs from these ancient explosions, delivered across space and time to become part of you. When you look up at the night sky, you are not looking out at a separate reality. You are looking back at your own origin story, written in the fire of stellar deaths and the afterglow of creation. We are the universe's way of becoming conscious of itself, finally able to look back and understand the violent, beautiful, and energetic processes that made our existence possible. And so, our journey through 50 astonishing facts about the cosmos's most violent events brings us to a final, breathtaking vista. We have traveled from the brilliant, self-destructing deaths of massive stars to the fleeting, focused fury of gamma-ray bursts. We have witnessed the slow-motion eruptions of active galactic nuclei and felt the space-time ripples from colliding black holes. We have seen how the serene nova is a precursor to a far greater explosion, and how the ghostly passage of neutrinos carries the true story of a supernova's heart. Each fact is a piece of a grander puzzle, revealing a universe that is fundamentally dynamic, chaotic, and yet beautifully ordered. The overarching theme that ties all these cataclysms together is the profound duality of their nature. These are events of absolute, raw destructive power, capable of sterilizing planets and tearing stars apart. Yet that very destruction is the engine of creation. Without the supernova that scatters its enriched guts across space, there are no rocky planets. Without the kilonova that forges gold and platinum in its wake, there is no material for future worlds or even the complex chemistry that underpins life. The immense jets from quasars and microquasars, while capable of halting star formation across entire galaxies, also help sculpt the cosmic architecture we see today. It is a cycle where endings are inseparable from beginnings, where chaos gives birth to order on the grandest of scales. Furthermore, we have seen how humanity has learned to harness these cosmic catastrophes as invaluable scientific instruments. The standardized brilliance of a Type Ia supernova is not just a spectacle, it is a yardstick that measures the expansion of the universe itself, leading us to the mysterious dark energy that defines our cosmic fate. The brilliant flash of a gamma-ray burst serves as a flashlight, illuminating the ancient gas clouds of the infant universe. The gravitational waves from a neutron star merger are a new sense, allowing us to hear the cosmos and confirming the origin of the heaviest elements. These explosions are more than just subjects of study. They are active partners in our quest to understand the cosmos, turning violence into knowledge. Therefore, the next time you find yourself beneath a clear, dark sky, take a moment to truly see it. That apparent peace is an illusion, a trick of distance and time. Right now, in some distant galaxy, a star is breathing its last in a blaze of glory, seeding future worlds. A black hole is feasting on a star, lighting up its galactic center. A magnetar's crust is cracking, sending a shiver through space-time. The night sky is not a static painting. It is a dynamic, ever-changing arena of titanic forces. We are the fortunate witnesses living on a planet built from the ashes of these ancient explosions, our very bodies composed of stardust forged in their hearts. It is a story that connects us directly to the most energetic processes in existence, a reminder that to understand the cosmos is to understand our own profound and violent origins. The universe is not just out there, its history is written within us, inviting us to keep looking up, to keep questioning, and to continue unraveling its deepest mysteries.